Alright boys, so the last we left off we were doing speech recognition, and I had the idea, hey, what if we used image recognition to recognize speech on a rendered graph of the sound waves? The same types of technology to measure the features of a graph of the sound waves visually should for sure be applicable to match the word to a defined word on file. For sure. I mean, it's the exact same thing. I'm confident this has got to work. And the advantage would be you already had to make computer vision, and if you're going to do speech recognition, if you could use the same code twice, you cut your work in half. So that's a huge advantage. Now, computer vision I've implemented for past projects relating to video game botting, but I only created very primitive image recognition. I'll show you guys basically how we did it. It's just very, very simple. We had, here's the number 4. You can see these 7s form a 4. And so that's like a little pattern to find the number 4. You can actually see the 4 right there. And so just, but the way we did it, we would take like RGB value from a color picker and start X, start Y on the screen where we'd look for that 4. No, actually, where we'd look for it would be a larger area, but that would be like just generally the width and height of this. But the main thing is 7s are where it's a match to the RGB value, and we'd have a little bit of leeway, like plus or minus 5 or whatever. So red and green, if those are high, and then blue is low, I think it makes yellow, or like a lime green. So this is like a lime green 4. So I'd actually be able to find this 4. And so that's how we did it for everything. Just 0s if it's not that color, and then 7s if it is. And then we would be able to pattern match this. But we want to create something much more robust, where pretty much like it would detect the change between the background and the foreground, and actually edge detect this and outline it. Once you can edge detect and outline, you then have your shape, and it would be color independent. You wouldn't need color per se, and it'd just be able to like draw it out, and then you would match the shape against the shape on file to get a positive match if it were a close resemblance to the overall shape. And so that's kind of the upgrade we're after. With this, we were just like, if you see all 0s, and then if you see 3 0s, 2 7s, and 2 0s, and then if you see 3 0s, 2 7s, and 2 0s, and if you see 2 0s, a 7, a 0, a 7, and 2 0s, if you saw that stuff, then it's a match. And it had to be like almost perfect. Maybe like 1 or 2 things could be off, and it'd say, well, it's a 92% match, we'll take it, it's a 4. So that's pretty much how we did it. But if you say like, oh, it only has to be a 80% match, it would get false positives, unfortunately. So that's how we did it. But we're looking to take it, to a professional level now. Hardcore. Now, I'm against neural networks. I'm against deep learning completely. I think the whole field is a joke to me. The fact that you have to train it on like billions of gallons of data is ridiculous to me. It's ridiculous that you can't like fine tune and tweak manually the rules that led to a bad result because there are no rules. It's just little weights, billions of little weights, and you just cross your fingers after countless tens of thousands of dollars of training have gone in. You hope the thing performs better. It's like just it's a joke. It's a joke that has produced something useful, shockingly. So it's it's cool. It's got utility to it. I use ChatGPT, but um, it is completely irrelevant to robotics as far as like having something that you can really dial in to work in your environment perfectly. And so, yeah, in so many ways, I just dislike all of it, all of that stuff. So I'm doing everything I do is explicit rules based AI. You could call it symbolic AI, you can call it good old fashioned AI. GoFi. So that's my preferred style. Gives you complete control. You make rules for everything. It follows your rules, so if it screws up, your rules were wrong. You need to add to your rules. Eventually, your rules become so robust, covering every possible alternative, that it's perfect, and it just does all the rules excellently and has excellent results. And then, it's not like you have to manually code all rules. You can have the robot generate its own rules as it learns, and in that way, automate the production of rules. But then, despite the fact the rules were automated in their production, you can go back and troubleshoot when it fails and see what rules led to the failure and then tweak the rules. So you still have complete control because you can modify and fine tune it. Okay, so right now I'm just doing research on computer vision, all the different tricks of the trade, all the different techniques. I want to understand them all thoroughly. I want to pick the ones I think are just really easy to grasp for me conceptually, and then that I think are very practical and very excellent. And I'm going to pick my favorite ones, and then I'm going to implement those, get it perfected, and hopefully create world-class computer vision. So this is a research day. I'm not going to be doing any coding today. At least I don't intend to. I have to eat. Probably gonna only do like an hour or so on stream, maybe, while I'm eating and researching. I just thought I don't want to not stream this because you guys need to see what I'm seeing. Like, be up to date on this research and how I'm using ChatGPT to learn what I need to learn, documenting how I learned it, where I've come from, where I'm going, and even just showing like how I coaxed what I needed to know out of ChatGPT can help people to see like, wow, that's a way to use ChatGPT. That's pretty cool. And they might learn something from that. I think the more time I spend with ChatGPT, the better I get at like getting the information I need out of it efficiently. So I disagree with, oh, you need this huge data set. That's not true. You get one example. You teach it. It's one image. You teach it how to identify everything in the image. And then you crop out some parts of that image and put it in some other image and make sure it can find that. And then you rinse repeat for every common image in the environment your robot's going to be. And then you generalize how you did that, you automate the training of that, and then he can expand it to various types of things. But you don't need to get huge data sets, no. It's saying this because it's biased toward deep learning and neural networks, which use huge data sets. We're not doing that. Explicit rules-based AI don't require large data sets. That's the beauty of rules. You don't need a billion little weights to somehow start obeying, which takes a lot of training. You need very little training because you're just developing rules by hand and then eventually automating the development of rules based on the original rules you did by hand. You're extending that in an automatic way. I like to read through it, see something that I want more elaboration on, and ask questions. Like this. When you say extracting features such as edge and corners, so you know, yeah, he's down there answering that while I'm up here reading for more possible questions I could ask. I'm working on today, researching computer vision techniques. ChatGPT is pretty dumb, actually. It has no common sense. It produces no novel ideas or knowledge at all. And it has no recollection of anything you talk to it about. It's only useful for being able to learn about research humans did that it read about. And just it's basically just a search engine. Hey, hold on a second.
Yeah.
Hold on. I'm very much looking forward to asking ChatGPT a million questions right now about computer vision. I have so many questions. It's like I could probably do it with the information I have now, but I want to learn like more about like what techniques are other people using in the industry and how could they possibly be implemented into my techniques to improve the way I've already come up with doing it. But I want to thoroughly review everything I know about computer vision, all my notes, all my planning. Actually, this idea of separating the image into many different grid squares and then processing each grid square with a separate exe process, i.e. multi-threaded. I mean, you don't have to do different exes, you could do more than one thread in one exe, but I just do separate exes because it's easier for me than setting up threads or whatever. I've never tried multi-threaded stuff, I just create more exes. That technique is a technique for parallelization of the task, which could speed it up because the processor then is possibly running on multiple cores, and definitely each exe has its own thread. So you get baked in multi-threaded that way anyways. Um, but now that I know how to use OpenCL to actually run calculations on the GPU, that gives you your parallelization right there, and it's even faster than multi-threaded, I believe, because it's taken all that burden off the processor and putting it on the GPU, and the GPU can run so many calculations so fast, all at the same time. It can run like 8,000 threads at once. That's like if you open 8,000 processes at once, and it will just do that for just as efficient as it possibly can figure out how to do. It will try to do it to run all the calculations you want. And so basically, we feed in pixels to the GPU in the form of an array of pixels. We send the array in, and it can run any type of testing on that, any type of modification on neighboring pixels or whatever, to run tests of like gradient changes or light and darkness changes or color changes, and then it can like see if those changes apply in a certain direction of neighboring pixels in order to establish an edge or a corner or a curvature or a straight edge, and it can just like go through, and then once it starts finding edges, it can see like if the two sides of the edges are getting into different colors or textures, and then it can like, you know, eventually work out all the different shapes and then figure out which shapes go to what, and essentially start to just separate the image into overarching groups. And you know, if you've got the image of what I'm seeing right now, you'd eventually figure out like, okay, that's the webcam, that's the monitor, that's the notes, that's the air conditioner, that's the background, that's the wall with some notes on it. Like, just breaking down images into categories and sections. Um, and then it can like, you know, ignore small details, perhaps, unless if they're nice for identification. So yeah, one thing is a lot of people create vision AI for like, this vision AI is to identify bananas in any image really well. I don't get that luxury. My vision AI needs to identify everything like a human of any image. It needs to be robust, applying to just anything. I mean, within reason. So, I need to come up with really generalizable techniques that work for most any image task. We want this thing to be able to identify everything, not just a thing in a picture, but everything. Break it all down. And we want it to be able to solve CAPTCHAs even. Every CAPTCHA. But one good thing is we don't need it to know how to identify like every type of object as far as like knowing what that is and having a name for it. Because like it's never gonna see ants. Like it doesn't need to know what an ant looks like. I mean, yeah, there might be ants in my house once in a while, but the robot can ignore them. We want it to be able to identify like every household object or every object used in like a DIY video, like tools and human hands, and identify the person cleaning the car with the rag and a bucket of water, like just, you know, macro elements, identify he's working on a car, identify parts of a car. He's going to be definitely a car mechanic, so he needs to identify anything to do with looking at a car engine or whatever. Or anything to do with laundry, because he'll be doing laundry. So this separate the image into grids step we can definitely skip because we know how to now use the GPU. That's going to really be a game changer, using the GPU. I believe a lot of guys in computer vision don't actually know how to use the GPU. And that's something that I'm blessed to have now learned about because I was creating my own 3D graphics engine and I insisted on making it so low level and making it from scratch. That led me down the path with ChatGPT to finding out, hey, if you want to do that, you want to talk to the GPU directly with your code, you need to use a library like OpenCL to talk directly to the GPU and run code on the GPU. And now that I have that ability in my tool set and my arsenal, and I've tested it and I've created code that actually does it, and I get it and it's easy, oh man, I'm going to be definitely doing all my calculations on the GPU. It's going to be great. One good thing is like, you know, if you're just showing it random images every time, yeah, it could take a while, but if you like have the robot in the same environment, you know, the first time it tries to identify everything might take a while, but the next frame looks the same. Like maybe if, you know, somebody's hand is moving like this across the frame, that's the only thing that changed. Everything else is the same. So it only needs to identify everything once, and then after that it's just taking note of whatever moved. And so the computer vision work behind that is kind of front loaded, and there's minimal work after the fact. So that initial scoping everything out is what takes the longest. So it's okay if that is a little heavy on processing. I'm willing to take that hit. Um, you know, we want to make it as efficient as possible, but ultimately it gets easier after that because environments don't change that much. Also, like if it's watching a how-to video, yeah, there might be cutscenes, like it cuts to the person talking, then it cuts to what they're working on, cuts to the narrator, cuts to something else. The cutscenes could be taxing a little more, but not if the robot is already like the cutscene is going back to a scene the robot already identified everything. If it can remember like those identifications and locations of everything, the layout, um, it would be able to like re-identify without having to like go through a lot of hoops to do so because it had just identified that. So it should all have that in memory still. So that should help it to not have to like redo everything each time they do a cutscene. As far as the calculations, identifications. So there's little tricks like that, I'm sure, we can try to employ. determining shape of each shape. The shape of each shape. Like, is the shape skinny? Is it wide? Is it tall? Is it rectangular? Is it triangular? Is it oval? I haven't thought you could go around the outer perimeter of the shape and like once every like hour on the clock. So there's 12 hours on a analog clock. Um, Once every hour or so, you just make a little dot along the outer perimeter of the shape, and you calculate basically the vector that points perpendicular to whatever that curve is. I guess that's called the derivative or something. Like basically like if you have a curve like this is the vector. Like whatever's like here's if it was just a straight line, the vector would just be like that. Like so whatever's like the thing that goes per perfectly perpendicular to it. So if it's a curve, it'll go like that. It wouldn't go like that. Like if the dot on the curve is where my fingertip is, it would go like that, like vertical. And then if you put a dot right here, then it'd be like that. So basically, like measuring those, what are those called in mathematics? I don't even remember. Surface normals? Is it called surface normals or something in 3D graphics? You definitely need to know that for like calculating lighting effects. I believe it's called surface normals. Um, Having the surface normals at each dot calculated, you could like describe a shape based on its surface normals going clockwise as you travel around the shape. And then compare that to a list of surface normals as you travel around shapes from file, and you'll find a match even if the object's upside down or rotated. The surface normals ordering would be a little different as far as like what's at 12 o'clock, but if you rotated it 90 degrees, the surface normal that was at 12 o'clock is now at 3 o'clock. But if you're going clockwise, it would still be the same pattern. It just started at a different place. So then you could compare the two and see, it's the same object, it's just rotated 90 degrees. It's just not vertically aligned. And so it would be able to match the shape, even though the shape rotated, based upon the surface normal comparison. I thought that could be a way of describing shapes and then matching them. That would be non-vertical oriented requiring. I guess that would even describe, curves and stuff. Seems like a smart way to do it. So it's like edge detection, and then that surface normal. What? Let me make sure. I'm using that word a lot. I'm going to memorize it, and then it's going to be wrong. Surface normal vector. The normal vector is often simply called the normal to a surface is a vector which is perpendicular to a surface at a given point. Yes! Surface normal vector! There we go! So what I'm saying is like we calculate, like let's take like this sphere here. Here would be a surface normal vector, here would be one, 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 here would be one. And you could like, once you have that, you could like list them out in an array or in a list. Like here's the first one, here's the second one, here's the third one. And then you'd be able to compare that to one of those array lists on file for the same object and say, oh, look, the surface normal list matches. Even though the color could have changed, the size and scale of the image could have changed, the rotation could have changed, but the change between surface normals from here to here to here, it just changed by, from here to here, it changed by 20 degrees, then it changed by 10 degrees. You'd be able to have the same changes, like acceleration of change, or linear change as you travel around it. You'd notice certain changes that would be the same type of changes. And so describing shapes that way could be really powerful mathematically as a way to like capture the essence of the shape with numbers in a way that can then be compared. The GPU would compare these lists against the other lists and be able to make matches. But we'd narrow down the list first of possible matches by like, well, this is a very round object and it's a small object relative to other objects in the frame. Maybe we could get some idea of size that would help narrow down. And the object, so then you'd go to the small objects folder of objects, and then you'd say, and also the object is like a yellow object, so you'd go to like yellow small objects. So now you're narrowing down the list. And then it's like, and this object has like a fuzzy texture, it's very smooth. If we could like determine that with computer vision, or it's hairy, then then you could get really specific. It's small, it's smooth, it's hairy, it's rounded. Well, I just described a testicle in accident. A small, smooth, hairy, round object. That wasn't my intention. That just happened by accident. Maybe it's because I was looking at this ball right here, and I just described a testicle by accident. So then, yeah, I would basically find out like, okay, yeah, that's the object, but it maybe have a small list of other stuff. Let's see, furry, small, smooth, like a small baby puppy or something. So it's kind of round or whatever. So it'd like have that or a testicle or a small number of small rounded objects that are hairy. And so it wouldn't have such a huge amount of work when it's now going to compare the surface normal vector chart as it travels, taking vectors once every couple inches or whatever as you travel around the object. It'd be able to not have to compare the surface normal vector chart of the item from the image with a whole lot of other possibilities from file. So it'd load all the possibilities, puppy, testicle, or whatever. It'd load like the small list of things that were from all those clues to narrow down. It'd load those into an array of a list of potentials. And then it'd take your array with the list of the actual item you're trying to identify, and it'd compare that array with the array of candidates, one candidate at a time, and it'd see which candidate is the closest match. And it'd even be able to say like, okay, this candidate is a 30% match, this one's a 70% match. So it'd rule out like, definitely it's not the 30% one. 70% one and up, maybe it is that. And so it'd say like, this is our most likely candidate. But if it were like, none of them were closer than 50% match or something, then it would be like, yeah, we just don't know what this is. And so it would like, maybe need to try another approach to identify that particular shape, Or it would just mark it as like, this is a shape we've failed to identify for now. And maybe that shape is a smaller part of an overarching shape, or maybe it's, the rear view of a certain object that we've identified before. We've never seen the rear view of it. And so it wouldn't have that one as a known. It could even try to upload that portion of the image to an image recognition online deal that could say like, oh, that's a spoon. And then it would be like, I guess it's a spoon. So it could appeal to or defer to other AIs for certain images it's seeing in real time that it just couldn't identify, and those AIs might identify it easily and quickly. So we would want to have that ability to like offload, like if we can't figure it out, the AI will automatically ask other AIs for help. And that would help a lot, even training it through time. That would train it. Because then it would like know, okay, now if I see that type of shape, I'll know that it's a spoon. And so I'm hoping to do that as well. But as it gets better with knowing like the majority of objects and tools and stuff, like just knowing, like just does a good job, it can identify stuff easily, it just gets really good, then it wouldn't be asking other AIs for help very often. That would go down with time, and it would just be really good at identifying everything through time. And I suspect the stuff in its normal day-to-day environment, because it's like, for a robot, it's going to be seeing the same room, the same tools, the same people. It's going to have that stuff down. It's barely, like, it's not going to need to look up much. Even if it's in a certain room, it will like load up common things it sees in that room. So when it's trying to identify objects in the room, it like doesn't have as big of a list because it knows what's in that room. So it doesn't, like, it would like not need to look up, all objects that could appear in any image. It would already narrow down, just show objects that appear in this type of room. And only if it couldn't identify something would it then expand its search to, okay, all known objects, is it something that we know of? So just having folders, organizing, like this is an object that you'd find in a house, this is an object that you'd find in the garage of the house, this is an object that you'd find in blah blah blah. So we would have like that type of thing to narrow down his search for matches significantly and have him quicker find it, because it's like narrowed down to that type of field, that type of scenario. Because like if you take a shape from an image with no clue, then he'd need to search like every known image in the universe. So what could it be? But that's not even how people are. Like, if you're in your room and you see something, you're like, what's in my room that looks like this? I think that's how our mind works. Like it will like think about things it's seen in your room before. So that's like a cheating way to like save on processing time. You don't need to think of everything you've ever seen, just things you've seen in this room before. So context of what room can help narrow down your total search. And I believe, we have context in our mind that like connects certain images to certain places, and that saves us time like figuring out what we're looking at in our brain. So that's how I think it has to be. So yeah, this idea of like measuring the normals like this as you go around the outside of a shape will be really good. If it could measure normals like of a 3D of a shape it's looking at on a, it's a 2D plane it's seeing from video still frame. But if it were able to identify like once it has an object, if it can locate, like in grayscale, like, oh, this part of the object's lighter, and look, there's shadows around the edges. The light must be around this area, so it must be like, the light would be like where this finger is, and it's shining this way, so it's right to left, and it's the light's toward us, like toward our camera. Then it would maybe be able to say like, this is a three-dimensional object, and these faces of the object are facing more away from the light. That's why they're not as bright. The faces facing at the light are brighter. And then it could get like an idea of like the three-dimensional shape of it, which adds like depth information. And that would definitely help it with like telegrammetry to like be able to create a 3D model of the object. But it might help it in some ways for object identification too. For computer vision, not just being able to make a 3D model of it, but also like help it like identify. Maybe. But then it seems like a lot of images in real life aren't this neat. Like in the computer graphics, like there's like one light source and really obvious shadows. Like here the shadows are really exaggerated, but like in real life, it seems like light is pretty uniform and like everything's like equally bright and there aren't really that many shadows like on the object. It only happened in like a dark room with one bright light source. That doesn't really happen in real life that much. So maybe that type of help and like understanding what it's looking at is unrealistic to expect. You would call that like an object that's like fleshed out, like just lights everywhere on it. There's no real shadow help going on. And if there is any slight variation from the light, it's like so minimal that it barely helps. Man, this is complicated stuff. When I think of like, how would it identify a person by their face? Facial recognition would be hard. Because I'm just working on like shape recognition right now. Helping like identify stuff based on the shape of the perimeter of it. Based on first finding the edges of it. But facial recognition isn't just that. It's also, how does that work? Let's see, it would be like, oh, maybe like it'd do the proportions of like the width between the eyes. So facial recognition is like, instead of like separating like the head, let's do a face. So like, yeah, this would be like our first step is like identify the outline of the head from an image. So it would like kind of make one of these. And I'd be like, that's a human head because, if you take the surface vectors, I'm drawing little vectors off it, like little perpendiculars off the curves. If you take that and then you compare it to other similar vector patterns like that of all the vectors that surround it, if you just take a vector once every couple inches, it'll be like, yeah, that matches the vector pattern. If you go clockwise, making vectors of that shape of a human head vector pattern model. And so that's like a great way to describe a shape, by vector patterns as you travel clockwise across a shape. So it'll be like, yeah, that's a human head. And then if it takes like even tighter vectors, it could be like, oh, that's the vector pattern of an ear. So we could do like big vectors, really spaced out to get like overall, but then like smaller vectors to determine like parts of that shape. Once you identify it's a head, you'd be like, this is the ear part of the head. So like that could help. That could be a technique. But then once it has this, then it would be like, okay, once we have like where the ears are and the top of the head would have a certain vector pattern, we'd we'd make sure that's the top. If like the head were sideways, we'd like want to rotate it vertical to set it up before we do face recognition. So we would rotate it vertical first, get it really nicely line centered. And then it would identify the eyebrow as a shape, the eye as a shape, and then the nose it'd be able to figure out based on that. And then the mouth. And then it'd measure like height from lower lip to bottom chin, height from upper lip to nose. And then maybe do the proportion between that. So this is like 2.5 to 2. And then width of nose to width of mouth, that'll have a certain proportion. And then like width of eye to width of mouth, certain proportion. It could like just measure certain proportions like that. And then based on the number of people it knows their proportions for those types of measurements, it would easily be able to say, oh yeah, that's so-and-so. Because you would have a finite number of people you're comparing to. And plus you could even narrow it down by like, he has brown hair, and it's parted right here. And the total number of people that have parts at exactly the 1:30 on an analog clock, or 1 o'clock. The parting's at 1 o'clock. With brown hair, and it's swept to his right, and maybe his widow's peak is this much taller than the eyebrow, but the other side doesn't have it that tall. That'd like narrow it down a ton too. Then you just go people that kind of have that type of widow's peak and hair part of that list. Now we compare the faces. So like, yeah, that would narrow it down real quick. If you don't, especially if you have a very small number of people. I mean, maybe like 50 people you can identify between. Now, if you were trying to identify between like billions of people for for like NASA or whatever, not NASA, what's it called, CIA or no? What's the technical one? The one that like looks at all our information, the CSA or something. The one that Edward Snowden outed. I don't remember what they were called, but yeah, those guys, like, they probably have one for everybody. They would have to be really specific, like eye color. Yeah, eye color would be a good one. But anyways, yeah, so that's how you do it. So facial recognition would just take a ton of measurements between stuff to get proportions. And that would differentiate one human face from another. That would help. I'm trying to think if that helps generally, like for shapes in general. Yeah, I guess the measure of like the tallest, so like, yeah, the widest part, like this is wider than this. It's like the measure of the widest part, and then another cross section of like the center line of the length of the shape and the center line of the width, and you'd measure the two and get the proportion between the two. That, even just that measurement, forget the surface normal stuff, that would almost identify just a face right there. But the surface normal would still it would tell you like this is a curving thing, because there's like a boom, a boom, a boom, a boom, a boom. And if their offset each time is like 20 degrees, 20 degrees change, 20 degree change, 20 degree change. Okay, this one changed like 30 degrees. You'd be able to like write down like 20, 20, 20, 20, 20, 20, 20, 30, 30, 40, 30, 30, 30, 20, 20, 20. So you'd like describe the shape as 20, 20, 20, 30, 30, 30, 20, 20, 20. Like, that's a way of describing a shape, and it sounds so weird. Like, what is that talking about? It's talking about the degree change as you travel clockwise around the shape between the surface normal vectors. It just seems like a smart way to describe a shape. So there's like kind of a lot of ways to describe a shape. I wonder if that's the best. Or maybe we should start out describing the shapes like the most general way, because the vector and pattern like describes like in detail like the curvature of the shape. A curvature pattern is what that's defining. But maybe that's like for like really fine tuning our search. But at first we could just be like, hey, this shape is like, if you just kind of took like a rough vector pattern, like just took like maybe 5 of them around a shape. I feel like that could start to give you like, oh, maybe 10, I don't know. If the vector pattern is changing like 20 degrees each time, like let's say the shape were just like a rectangle, what would that kind of vector pattern be? So that would be like boom, boom, that changed 0%, so it'd be like 0, 0, 0, 0. The next one just suddenly changed by 90 degrees, so it'd be 90, 0, 0, 0, 0, 90, 0, 0, 0, 90, 0, 0, 0. So that would tell me like, if you get a bunch of zeros, that's a straight line. And then if you go from a 0 to a 90, you know you just hit a corner. And then if you got like 4 90s, you know it has 4 corners. And if it had more, like a bunch of zeros and then a 90 and then a few zeros, then a 90, then a bunch of zeros, then a 90, you know the one with the bunch of zeros was longer edge. Because it was more zeros, which indicate a straight edge. And so that would say like, oh, we just described through our vectored pattern clockwise measurement, which could have started arbitrarily anywhere, it would still give you the same type of pattern of, we got 4 edges that made 4 90-degree turns and had straight lines in between. Even if it wasn't a 90, if it was an imperfect, like a stuffed animal rectangle, it'd have some like that, but then it'd be like that, and then it'd be like that. But they'd still be like plus or minus like 10 degrees of each other. So like overall, you would get this idea that, yeah, that's pretty rectangular, even though it wasn't a perfect rectangle. It could have been like jaggedy, like a rectangular rock. It would still average out to about 0-ish, or it'd average out to like 5 degrees of change over time throughout the whole edge, because it's roughly straight. And so that would describe a roughly straight line. So like that would still describe rectangular then. And so this vector pattern thing really seems like it could describe a lot of stuff. For shapes. So the zeros are really cool for like straight edges. And then like significantly changing, like that face we had. This would be like boom, then boom, that's a 20, that's a 20, that's a 20, that's a 20, that's a 20. If you're having that many 20s as you travel across it, you know it's curving. And that would actually describe like the severity of the curve, the smoothness of the curve based on these types of measurements with vector normals. And so that would really be a great way to like get the idea of a shape through the use of numbers. And if you abstract the shape then to say like a gently curving half circle is the top, and then you've got significant changes here. I don't know, you could like create verbal written descriptions and then use the written descriptions of shapes to look up other shapes that had that written description. So now instead of you having to look up a pattern match, you'd just be able to look up the written description of the shape, and then you could have all shapes that match that description, and it'd be like a bunch of people would be in there, a bunch of heads or something, or even animal heads that were similar shaped, like maybe monkey heads or something. And so written descriptions could then have shapes that match that description in that folder, and then you'd be able to do like a tighter vector normal comparison or start comparing the colors of the shapes and different stuff to get like which object in that folder is a dead-on match, which one's the closest match based on different types of measurements. We can measure different types of things, different type of proportions. So like working from general to specific, and we could have multiple different avenues. Like maybe if this was just all white, we just go to our all white shapes folder and see what's a match. So we could have like multiple paths that lead to a match, and it could like just try out a few and see what's the best, and it might get lucky and just find it really quickly. So it doesn't just have to have one type of classification. We could have different ways of measuring it, different ways of finding. Like for example, if it's in a room and it sees a small object on the floor, right away we could go to like, objects in a bedroom folder. Objects in a bedroom that are very small. Now context helps there because the robot knows it's in a room, it knows it's in a bedroom, it knows that this object's on the floor, and it knows this object's very small. That helps a ton because then we could have a list of very small objects. But then like if you're just looking at a random picture just delivered to you from online, you wouldn't have that type of context. This could be a tiny, tiny, tiny postage stamp of this guy's head. We don't know how big this is. There's no ruler next to it. This could be a small painting the size of a quarter. So we don't know how big it is. But if the robot's in a known environment, it would know the scale of the object within its environment. And that would help it to then look up the object by the object's actual size. But with nothing to show scale in any of these pictures here, we don't know what size these faces are. These could be microscopic, or they could be... This girl's head could be bigger than the planet Earth. We don't know. So, but the robot would know that like based on like footage he's seeing from inside a room, once he starts establishing, where he's at and what he's looking at. That gives contextual clues. And so basically we're thinking of different ways you can narrow your search for matches. Sometimes he won't find a match, but the biggest thing is if you have an object, let's just say we try to match this object against 1 billion known objects, and all billion known objects are in the same folder, and he says, does this match object 1? And it like does a bunch of calculations. No, it does not. Does this match object 2? Does a bunch of calculations. No, it does not. And it has to do that for all billion objects. That would literally take possibly like years of processing time for it to say, we could not find a match. Or we did find a match. It was number 750 million, object number 752,543. That's the object that matches this. That's bad. So that's why we want to come up with ways to store objects in folders and then access folders that pertain to this object based on what we do know about the object. So that's why I'm coming up with different ways, like small objects, objects in a room. Based on the context, we know it's in a room, we know it's small, maybe it's this color, it's this texture, all kinds of little clues about it that would narrow the folders that we'd be checking in. So that would lower his total search to compare it to. And if you can do that, then you can get into real specific, heavier calculations like learning all kinds of measurements and all kinds of things about it, comparing it to those things in the folder. And it can afford to do that because you narrow down so much what it's checking against that it can do more measurements for each. Like, is it this one? It could look at a bunch more stuff to see. But you'd have to already narrow down like similar objects first, or objects that could match it. Narrow it down a ton, then it could do like way more calculations at that point. So we have to have like it broken down that way. So we save processing time. The more efficient we could design it, the better. Because we want it to go fast. Speed is king in image recognition. Because like, you know, most people will just take like a video and their AI for vision only detects a human face in the picture, only detects a red ball moving around. You always see that in these demos. And it's like, no, we want it to detect every single thing in that whole image. Everything. And then create a 3D model of the entire image. We want it to be able to replicate whole scenes in 3D. Because we want the robot to be able to navigate through it. And so it needs to create a vector space representation of what it's looking at. So it would create like a video game world of whatever it's looking at. If it's watching a movie, it'd create a whole video game world of that movie. If it's looking at my webcam, it would create a whole video game world of my room. And that way it can simulate walking through that world and interacting with it. And explore it. And also that way it can just look at a movie, create a video game world of every scene in the movie, and then you'd be able to create video games so easily because all of the art assets could be just generated from just watching a movie clip. All the art assets in the scene, the pottery, the clothing, the decorations would all be able to be reproduced in 3D with 3D models and textures and everything, all immediately. And then that could be loaded into a video game world or a movie world for a movie it's making or a video game it's making. Because I want my robot to be able to make video games and movies based upon watching videos. And then it would be able to gain all of its art assets from watching a video. It also needs to be able to watch like DIY and how-to videos, recreate the world it's looking at in 3D, and then insert itself into that world and itself be the actor doing what it sees the person in the video doing in order to mime him, and then in order to be able to have the ability to replicate the skills that this actor or mechanic or whatever in the how-to video is demonstrating, the robot would immediately have the same skills because he would be able to reproduce the 3D scene of the how-to video programmatically and then be the mechanic in the video. And so he would know exactly, he'd be able to copy all the hand movements he saw, copy all the tool grabbing and usage, identify all the tools, everything in the video frame by frame, and be able to do the job it sees the mechanic doing. And that's so important because then the robot would be able to teach himself how to do novel new tasks based on watching a video, just like a person can do. And so the robot would be able to obtain new skills by watching YouTube videos, like a person can do. And that way you don't have to teach the robot how to do everything. The robot teaches itself how to do new things. And that is the holy grail of robotics AI, for sure. That's as good as it gets. Impossible to beat. Okay. For me to say out loud, like, the dream of having the robot be able to watch videos and pull out all items, identify everything, reproduce whole 3D worlds based on watching a video, which is in 2D, obviously, and be able to reproduce that in 3D and then make a video game from it or make a movie scene from it, um, and be able to traverse through it and put himself into that scene and interact with the stuff in that scene with the physics engine. Um, Imagine if it like if you could press pause on a movie, the robot reproduces the whole movie in 3D with photorealistic movie scene, and then the robot jumps into the movie scene. He's walking around smiling at you, walking around the scene, inside the scene, and then he starts like beating up all the actors in the scene, and they start running away. And it's all done with AI, and he like beats them all up, and then he starts laughing, and then the scene ends. Like the robot could do that. That would be crazy. Or like the movie scene has like two people arguing in a bedroom, and the robot jumps into the scene, smiles, and waves at the camera. The scene is paused. The robot's the only thing moving in the scene. The robot walks over to the bed in the scene and makes the bed, and then presses play, and the robot's standing in the scene looking back and forth at the actors as they continue arguing now. But the bed's made in the background. The robot's standing in the scene. He just inserted himself into the scene. And he just continues to stand there while you're watching this movie. The AI could literally do that while you're watching a movie. It could, like, just do that. That's super crazy. That's trippy. So you could just have your robot inside any movie you're watching. He'll just imagine like you're watching The Matrix or something, and like, you know, Morpheus is talking to Neo, and they're walking through the city streets. You remember the woman in the red dress walks through? You could have like the robot walk up and punch the woman in the red dress, and she gets knocked out, and then the robot like smiles at the camera, then walks with the rest of the people wearing a suit. Um, like it just changes the movie in real time while you're watching the movie. The robot's like just trolling, just being a clown, making the movie funny, and like adding comedy to a serious movie. Just editing the movie on the fly. You could like be the ultimate troll. You would you would definitely like want the robot watching the movie with you so he can like mess up the movie and be a clown during the movie. That would be insane. And we'd have the tech to do this if we can pull off this type of stuff. That'd be like stretch goals, things that could be done. Um, with this type of technology. Wow, that is crazy. So like by me describing like stretch goals, like how far you can take the technology and having a vision for that, that will dictate and shape the whole process from the ground up designing the vision system. Because we know like what we're heading for, what would be our goal, and then we'll design all the processes to get us there, having a clear roadmap then. If you don't really know what you're doing or where you're heading, you might implement a system that's too narrow or too short-sighted. We want a system that's really robust and will be able to take us all the way to that type of goal. So that just helps us like rule out certain things when we're making decisions as we design our system, that's all. And the fact that it'll be able to solve any CAPTCHA is pretty fun to me because CAPTCHAs can hinder me and my robot from doing what we want to do. We want to be able to use online services and stuff for the robot's benefit and not be blocked by any CAPTCHA. Now, you know, a malicious actor could do that and then like DDoS somebody or whatever. I'm not a malicious actor. Like I'm just going to be using the services with the machine using it to help me do like legitimate uses, not like harmful. not like hacking or trying to crash somebody's server or something. So the CAPTCHAs are put in place to stop malicious actors and trolls looking to like crash a server. They're not put in place to stop somebody from legitimately using an AI to like use the service or list something for sale or check something for the operator of the AI, not in a way that's going to harm the website or anything like that. It doesn't harm anybody. It's just basic office work, basic just helping out business use. So that's why I have no problem solving AI. It's not like I just wouldn't want to teach other people to like hackers to solve captchas, I guess. Anyhow, yeah, if somebody is skilled enough to solve like hard captchas, then I doubt they'd be a hacker. Like they would move on to like legitimate AI work, I feel like. Anyhow, um I'm picturing when I read this, you just searching around to see like little blobs or clusters where you see something changing. Let's look at like an example. So like, or okay. Um, so here's what I'm thinking. Let's select a color like some type of like, lime green seems like a good color. Okay. So we would be like duh duh duh, just doing a little test. Each time I say duh is a test. Test, test, test. Nothing much is changing. And we're just drawing like a random line across the whole image. Duh, 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 nothing much. Oh, what do we have here? And then it'll be like, And it'll be like, okay, it just changed from light to dark pretty quickly. That would be, in computer vision, last night we found out they call that like a intensity change. So like mark it. And then like, hmm. Seems like if the intensity change was this way, it should probably do like a vector. And then it should be like, okay, so that, because like the left side was fine, then the right side got dark all of a sudden. So that would mean like the change happened from left to right. That's why the vector's that way. If it happened like this, boom, if something was here and something was like that, and we been, you know, searching this way, boom, boom, we'd find the change here, and it went from light to dark. So then our vector would have to be this way, going up. But since it happened from right to left, the vector's pointing to the left. Um, and now we should do like some tests locally where we just go from left to right near it, like these, and we would find, ooh, here's one, and here's one. And so then it would, like, you know, start getting even more specific since it found a consistency there. It would test, like, you know, like test once every few pixels. And it'd be like, yep, we got a line. And then it would just keep doing that, now testing like once every few pixels, seeing the same change as we go left to right testing. And it would just start to be able to outline following it. And seeing consistently. And it would, no, we won't do the surface normals yet. Or maybe we should. I would say, okay, we stopped there. And then it'd also go down the other way. And then, yeah, I'd still see a big change here. It'd probably stop there. So it would have been able to mark that. Maybe it could continue because it would like kind of lose it, but not too bad right through here. It'd be a weaker transition, intensity change. And then it'd be like, ooh, we've just picked up the trail again. And then it would probably start following this way too. So I think even just based on that, it could even say like, that's a long line, this and that. It could be like, let's test that curve. No, that seems premature. I was gonna say let's test that curve against curves patterns from file, but it's like no, that's not right. I think it'd be funny because I'm saying like it could already probably detect that that's a human just based on that curve. If we take the vector normals on that line, that would match the profile of the left side of a human head every time. But we don't want to do that like the first shape we find. But it was a significant shape taking up the majority of the entire viewing pane of the entire photo. Maybe that would be something you'd consider doing if it were such a substantial shape that took up such a huge part of the photo. Maybe you would just look for something like that. That could be like a trick. I mean, if we already identify, okay, this is a human face, that would be pretty sick, like, to do it that fast. Not that many tests, not that many calculations were already taken at that point. Um, but that was just supposed to be like one slashing line going across, and then we would do like, you know, other slashing lines just randomly, just taking nice cross sections, um, like this, just like kind of, oops, kind of mapping out, um, the whole scene. It's kind of like broken glass. And each time it does this, it's doing tests of the pixels just on a line. And each time it finds like an intensity change, i.e. significant color or significant brightness change, it would like maybe start tracing out from there, and it would be able to find quickly. So it wouldn't even need to draw that many lines before it'd like find like, you know, the right side of the profile. It would mark an intensity change here, and it would immediately draw up the hairline. And then it'd be able to find like how these lines intersect, and then it'd be like, oh, this is a shape. Like, oh, look at this. We've got, you know, the hairline intersected with the outline of the head, and that completed a shape. And then it'd check inside that shape and be like, hey, look, it's all um, kind of the same color and same group of colors, same pattern. So then it'd be able to like kind of, you know, fill that in. Maybe it could do this visually as we're testing for debugging purposes. It would like it would say like, we found a definite shape here, and that kind of shape is very familiar. It'd be like, yeah, it's probably hair on a human male. And you know, it'd be able to find um, yeah, it could be like if it's brown or two different tones of brown, and it has this kind of shape, and it would mark that shape by like the vector normals like we talked about. Like, you know, the whole um, little test, that's a vector normal, 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 that's a vector normal. So this one would be like BAM plus BAM. The difference degree of change of these two vector normals is like, this one's going up more, this is a little more out. That would be maybe a 5 degree change. The difference between this one going out and then this one going out is probably like 7 degree change. And then difference between that one and that one is like 20 degree change. Difference between that one and that one is like 15 degree change. And then if it marked one right here, the difference between that and that is like 70 degree change. Just wonder if that pattern would be able to describe this in a repeatable way. But like another person's head might say 6 here, might say 8 here, might say 16 here. So then it'd be like plus or minus 2 then you'd have to do. Or plus or minus 5 degrees to get. Okay, yeah. So yeah, because you wouldn't be able to find it dead on. But like if it started here, like if the person were to rotate their head 40 or 20 degrees to the right, then if you're starting like at the top of the shape and he rotated it, like let me show you what I'm talking about. Like if you did this, he should still be able to identify the blue shape, right? The question is, does that blue shape just changed its orientation? But how do you get a match to identify them? Because now it's different. Like this is a downward facing C, and then this was facing C at this angle. And let's just say we arbitrarily started measuring, you know, like right here. His number for the shape on file would be like, well, hold on. 5, 7, comma 20, comma 15, comma 70 of just like that side of it. We didn't finish. And let's say here would be like, let's say he started measuring here the surface normals of the shape. And let's say this one to that one, the change of surface normal, that'd be a 0 because it's flat line. 0. This one to this one would be 70 degrees. Okay, this one to this one's change would be about 5 degrees. And then it would start 5, 7, 20, 15, 70. So then this one would look like this. 0, comma, 70, comma, 5, comma, 5, comma, 7, comma, 20, comma, 15, comma, 70. Now, if you compare these two, there's an offset because it was rotated, but then they start matching later, but it didn't match at first. So if it would need to compare with different offsets then, and also like plus or minus like 5 degrees for each one. So if this said 7 or 8, it would still be a match to this. So it'd be like a loose comparison of the two. Looser would be like plus or minus 10 degrees on each one. If it's a match, we'd just say. So it'd be like, if it's not a match, so like, okay, let's say, oh yeah, so this could be it. We could be like, okay, 0 and 5, is that a match that within 5 degrees? Yeah, so it'd be like 1 is a match, it'd be 1. 70 and 7, is that a match? Is that within 5 degrees? No, so that'd be a 0. 5 and 20, is that within 5 degrees? No, that's a 0. 5 and 15, is that? No, that's a 0. 7 and 15, is that? No, that's a 0. 20 and 70, is that? No, that's a 0. And then, since we kind of ran out of numbers to compare, because this one only had a few numbers recorded, we didn't do the whole surface normal change algorithm. This is 1, 0, 0, 0, 0. So that's 1, 2, 3, 4, 5 zeros and a 1. So that's 1 hit and 5 misses. So that's a match of 1, 2, 3, 4, 5, 5 and 1. Let's say one, wait, 1/6, is that it? Yeah, 1/6, which is, what's that percentage? 20 times 5 is 100, that's 1/5. So 20% is 1/5. This is 1/6, which is even less than that. So let's say like that's like 15% match is what we got. And so that's like, no, that's not the same shape. It's only 15% match. But it is the same shape, just rotated. That's why then our algorithm would need to do this. It would say like, okay, that didn't match. But if we start somewhere else, let's bump it over and try again. So do the whole thing. And it'd do 70, and that would be, so that would be a 0. 70 and 5 would be a 0 because that's not within 5 degrees. The 5 and the 7, that's a match. The 5 and the 20 then is compared. That's not within 5 degrees. That's a 0. The 7 and the 15, is that within 5 degrees? No, that's a 0. The 20 and the 70, is that within 5? No. Okay, so then that's all we had to compare. Wait, no, is it? Wait, what? Oh yeah, because we're starting with the 70 comparing this time. Because we moved it over. So it's 1, 2, 3, 4, 5. Comparisons only can be made. And so 1 out of 5, that's a 20% match, a little closer. But we define it has to be like, let's say, 80% match or something for us to say, like, yeah, that's pretty much the same shape. Okay, so then we do, the algorithm says, okay, move it over again. Okay, we'll try it again. And then, let me move our calculations up a little bit. Or I'll move these guys down. So then, we're like, okay, 5 and 5 compared, yeah, that's a match. It's within 5 degrees. And then we'll do 5 and 7, is that a match? Yes, that's within 5 degrees. And we'll do 7 and 20, is that? No. And then we'll do 20 and 15, is that? Oh yeah, that's within 5 degrees. And then we'll do 15 and 70, is that? No. Okay. So that one, where basically we started with the 5 of here, this 5, and then the 5 of there, we called it a match because it's a, oh wait. No, that's 3 out of 5. That's a 60% match. That's not good enough. But it's going to check them all. So then it'd move it over again. This is where it gets super awesome. Basically, it's rotating this head more vertically to match it. It's rotating the shape by doing this. We're like testing different rotations of it. So then that's what it comes out to being, basically, essentially doing. It does this, and then it compares, and it's like, oh snaps, 5 and 5, 7, 7, 20, 20, 15, 15, 70, 70. That's a 100% match. 1, 2, 3, 4, 5. 100% match, and it's like, oh snaps, no more work needed. This shape is a 100% match to that. So that way we can store this shape on file as just a series of surface normal vectors. The degree of change between each one as you travel clockwise around it. I think that actually works. As a way to describe shapes. That's sick. I think we just figured it out. And so like that's how you store shapes numerically. Describing the shape. Describing like literally. Every bit about the curvature and the changing, everything about a shape is in that. It's like encoding it. I feel like a genius right now. Like theoretically I was like, oh, that should be a way to store the shape, but now we just created an algorithm for like actually testing that theory, and it's worked super well. It basically enables you, any scale of that shape. If you made it smaller, if you rotate it upside down, it will still give you a match because the scale, even if you made the shape wider, like the second guy, um, even if you like did that, it would still be like a 90% match, I bet. After we like redid the surface normals based on the slightly different skew and everything, and it's bigger and everything, but that's not being taken into account. Or is it? Wait, there'd be more measurements taken though. We have a longer string of numbers though. So the change hit would happen in a different spot. Uh-oh. But wouldn't it be just repeats though? What I'm getting at is like, imagine we're like, it got substantially bigger, right? But then, so then we would be taking like way more measurements in between. There'd be more of these if we're just taking it at a certain interval. But then it'd be a lot of repeats. So then there'd be like, let's say there'd be like 0, 0 added in, and then the 70, and then there'd be like a few more of those, and then there'd be like another one of these, and that 20-degree one, 20, then like let's say there was 18, a 15, or like a, no, 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 there'd be like a 20, then like a 3, 15, and then a 2, but these are the same shape, just different size, more measurements. Um, Actually, maybe like this would be like a 2. Would it come out to be that? Let me modify this one a little bit too. Let's do like a 2. Um, Seems like th this number getting longer says more about the size of the shape, and this being shorter says the shape's smaller. Because we took fewer measurements across the shape because it was a smaller line, but then the longer the shape, the bigger the shape, we would happen to have taken more measurements. But in both cases, it's the same shape. But this just says, hey, this is how much longer the line was. So the lines get longer, the curves get longer, but it's the same curve. And it would need to still be able to tell us it's a match, even though the curve was longer. It's the same curve. More or less. I mean, I skewed it a little bit, but let's just say it's the same curve. Because I didn't change the numbers. We just added in-betweener numbers. Well, let's think about this visually. 0, 0, 0, that's a straight line. 70 is a big change. And these are more or less straight line, not really changing much. The 20 is kind of a bigger change, but not that much. Yeah, that's when it starts tilting downward more toward the ear. And then another downward tilt really coming in from the ear. And then the 70s where it makes the big turn to start climbing back up the face toward the widow's peak. So would you be able to condense these two down to their essence by considering all major curvature changes to be a feature, and then do some kind of feature extraction, and then compare the features extracted from both to do our match? Okay. So Or would we just describe it? That'd be weird. So then it'd be like, or would I then? The slight curving 2015-70 then matches up, right? Perfect match. Even though the numbers are way different, if we grouped anything less than like a big change into slight curving, or anything that all zeros is straight, or we could have like straight, mostly straight, that type of thing, and then major changes just marked. There's like minor change in between the major changes. We just ignore it. It's not long enough to consider a line. It's just like a tiny segment between major features. A funny thing is like we should be able to go take away the image and then go back to the shape from just the description. So if you're like, oh, um, oops, let's see. What the heck? just trying to make room right now. Wouldn't that almost be like proportional too if you said like, yeah, straight for what? It was 3 out of, let's see, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 3 out of 15 is what? Point 2 or 20% of the time, so let's just say point 2 was straight. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, 1 out of 15. .06. .06 was 70 degrees. Slight curving. Actually, maybe we don't even have to say that when it's just a big angle change. We're just marking angle changes between gently curving or straight lines. So you wouldn't even need that per se. Slightly curving. 1, 2, 3, 4, 5, 6. 6 divided by 15 is 0.4. And then 0.06. The 15 was... Actually, we could even put the 3 in as a 0.06. The 15 is a 0.06. The 2 is a 0.06. And the 70 is a 0.06. I wonder if here then the slight curving would be 3 out of 1, or 3 out of 4, 5, 6, 0.5, and then the 20 is is 1, 2, 3, wait, 1, 2, 3, 4, 5, 6, the 20 is 1/6, 0.16, the 15 is 0.16, and the 70 is 0.16. So the straight we didn't even mark on this one. But the slight curving, 0.4 of the time though. Is this making sense to you guys? Seems like... Slight curving 2015-70, slight curving 2015-70. Um... If, like, the head is jagged, I was just thinking, like, at a real small level, there could be, like, surface normals that are, like, like, let's say, like, it was, like, that. Surface normals could be all over the place. Like, this one would be like this. This one would be like this. This one would be like this. This one would be coming out this way. This one would be coming out this way. Then this one would be coming out this way. This one would be coming out this way. Like, we'd kind of be like having all over the place. But then if you average them across like a segment, it'd still be like the normal that like these other red ones. So you would want like real close together stuff to average out, to like smooth it out, and then that would give you like your normal uh you know, like overall surface normal from that little section. So I'm just thinking like of little things where this could go wrong. That would be like a solution for that. The idea here was like, yeah, point uh so like slight curving 1, 2, 3, 4, 5, 6. So like 3 out of the 6 were curving, so that's half the time. And then the 20, the 15, and 70 are the major changes that occurred, which happened 1/6 of the time, so that's 0.16. Um, so like half the time slight curving, half the time slight curving, 0.4% or zero point 0.4 of the time. And then 20, 15, 70 happens. So then even though more measurements were taken on the larger shape, the overall trends, if we could extract the trends, you could still match it to each other, even though the original numbers is like way different. It's still the same line, just bigger. Or would you just be able to downscale it? Or is that it? That is downscaling. this just downscaling? Or simplifying? What's super powerful about this is like we only measure a little part of this overall blue shape on the smaller picture, and then a larger part on the bigger picture, and we're just being able to see like, hey, can we even match a fragment of a shape to say, hey, it's this whole shape? That's powerful. Can you imagine like, so if you even see part of somebody's head or part of somebody's hand, just by matching the curvature based on the surface normal pattern, even if the hand is rotated in a different part of the picture, a different scale, and it's just a fragment of a hand, it would be like, yeah, that's the curvature of the knuckle of the hand. Like, that's how powerful this would be at matching fragments of images. Like, this is like super next level. If we can get this type of thing to work for matching like common curves or something. Not even just curves, shapes in general, because this thing handles straight lines, hard turns, every kind of shape measurement. This is great. You could even say like, rather than slight curving, we could even say like, if we're just trying to group minor changes in direction, we could even add them. So that's 6, that's 11, 12, 13, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So that'd be like 30 degrees of change over a 0.4 segment. And then over a 0.6 segment, 0.06 segment was a 20 degree of change. And then over 0.06 was a 15, a 0.06 was a 70. Okay. That would take the verbal description out, though. Might be okay, because that's, if it's 0.4 of the time, it changed 30 degrees over that large of a thing. Oh, and look, if it was like if it's changing like that, or like, wait, if they're going toward each other? If they're going away from each other? If they're same, it's 0. If they're going toward each other, though, that'd be a negative. Wow. So a negative would be convex. A positive would be, no, concave would be positive curving numbers for these numbers. But convex, if it changed and flipped the other way, it'd be negative numbers. We just added this segment up to a 30. I was just saying if there were negative numbers in there, that would like knock it down though. On the average. Because we're averaging, I guess, then. We're averaging a segment between major change angles. And we're also measuring the length of the segment, proportionally speaking, with a 0.4 out of total. So this like curving would be 7 plus 5 plus 2, which is 14 for that whole segment, which corresponds again to 2, 5, and 7. That would be like this little portion of the head was a 14 degrees of total change for that segment. Um, huh. Aha! So like, I figured it out. So like, so let's say, we're trying to match, um, we know that starting at this 70, which was right here, where it stops being the flat line, is where we're trying to match that curve to this curve, even though it's larger, so more measurements were taken as far as surface normal derivatives or surface normals. There were more of them because it's a bigger shape, because we scaled it up and we rotated it. So the rotation we want to still match, even though it's bigger and it's rotated. And so we know that this number should match with everything starting after this 5. So this should match this. Okay. Now, oh shoot, I lost my thought. No. Yeah, so this 0.4 was 0.4 out of like all these numbers. But since we're only taking a fragment of it, he'll know, based on the total number of numbers he's comparing to this, that it's a lot bigger. So he'll do a ratio thing. So like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 6 versus 11, he'd have a multiplier there. So um, 6 is to 11 as 0.5 is to, or no. He would take, since he's just measuring this section, this slight curving would actually be um, 1, 2, 3, 4, 5, 6 out of 7, 8, 9, 10, 11. 6 out of 11? Wait. Yeah, first he'd have to, since he's blocking out a section of it. 6 out of 11. Let's see. Well, let's just pretend it was 12. So it'd be two times as long, is what that tells us. So like 1.8 times as long. Yeah, 1.8 times as long. But we're saying if they're still the same general shape of that portion of a line of a shape. Does that line have the same shape as this segment of line? This one and this one. And so this is 1.8 times longer. But is it the same line? So he's going to say like the section leading up to the big 20 is a section of not much change, described as 14 degrees of change, a slight curving line. 0.5 of our whole line is that. Does he have something similar? So he'd say leading up to his 20 is a series of numbers that add up to 30 degrees. But actually it'd be less than that, since it is the same. I just kind of made up numbers. That would kind of ruin it. So let's just do like 501. That's minus 5 would be 25. Let's say this one's a 2. That'd be another 5 off. That'd be 20. That'd be 3 off. That'd be 17. So that's 17. Okay. 17 degrees of total change. 5, 10, 11, 12, 13, 14, 15, 16, 17. Now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6. 6 out of 11. It's 0.5. Nice. Oh, come on, the heck? Okay. So that's 0.5 we said. Since we were just taking a segment, we're comparing. And we chose that segment based on a commonality potential of like a section of not much change, or well, I guess we would just test like random segments, like same size segments or bigger segments, to see if we find matches. This 25, 23, 15 to 70 even could potentially be a match-ish. No, it wouldn't, because it'd be like 0.5, 0.16, 0.16, 0.16. Whereas that, if you just started like here, it'd be 1, 2, 3, 4, 5, 6, 7 total. 2 out of 7 would be 0.28 of it was matching the slight curving. 0.28 of it. Whereas this was 0.5 of it. So we'd want this longer stretch where 0.5 of it was slight curving, aka 17-degree curve. And then this slight curving of 14 degrees would be like plus or minus, let's say 5 degrees, we'd say, yeah, that's a match. So then if 0.5 proportionally of the segment is 14 degrees, 0.5 proportionally of this segment is 17 degrees, we'd say, yeah, that's a match, because the degrees is minus plus or minus 0.5 degrees of change for a 0.5 proportion of the total segment. And then we have our matching 20-degree change measurement. And then the 3 and the 2 are insignificant because it's just a little thing. So we would let that slide. Or even just add them in. So this would be a 23 and this would be a 17, which would still be a match, with the 20 and the 23 being plus or minus 0.5, or plus or minus 5 degrees, and then the 17 being plus or minus 5 degrees, and then the 70. So if it's like really small and only one, we would just add it into a neighbor. And then if it's like really small and a bunch of them, we add them all up and say, you know, the proportion of the total line measurement we're doing. So we're comparing the proportion and the angle change. And this does not matter then how much you rotate. The proportions of a stretch of a segment of line, the angle change with proportion, this should still match that. It's the same curve, no matter how you rotate it, it's still the same curve. No matter where you move it, it's still the same curve. We're trying to curve match. So we could have like a lot of familiar curves that are popular curves that would match, that would be memorized. Because you're not always going to get the full object in the frame. A lot of times images are clipped. Like in self-driving cars, if you just saw a bumper sticking out from behind a building, if it recognized the curve of a bumper, it would be like, that's a car. Like, bro, that's a bumper, that car's about to pull out, we gotta be careful, we gotta keep an eye on that, that's a car there. Whereas if your image recognition is just like, I don't see a car has four wheels, where's the four wheels? Like, no, you need to be able to recognize even a recognizable curve. Humans do that. We would recognize just a little piece of a bumper because we know that curve. Plus its height from the ground. So like if you see that curve at that height from the ground, that's for sure a bumper. So that could be a clue as well. So this type of technology to even just curve match is very important. We're not just trying to get a full image match, we also want the ability to curve match. A curve from file with the curve seen in a scene. Would it be easier to actually, what if we did this? Like, okay, it's like, this might be easier than what I just said. What if we literally, alright, um, oh, that would be kind of weird though. Yeah, what I said was even better. I was just thinking like, if you just wanted to straight up compare, you would just try different sizes and do the full test again and again. But that would be way more processor intensive than what we were just saying, where like, you pretty much create rules like, if you have very small changes, that's pretty much like just a slight curving line. You just add them up, they add up to 17. These 2, 5, and 7, that's a slight curving line, adds up to 14. And so you just define segments as slight curving, and then you mark out any type of major change, of course, as like a feature. Significant curve change features. You just join in nearby ones where it doesn't change much from there. And it's not like long enough to be considered a feature of like a line between curves. It's just like a little one-off. You just join it maybe. Or like if you were comparing like 2, 5, and 7, but you see clearly we're comparing a larger line, you just group smaller ones up to the 20. So first you just compare these like, where's the first major change? It's like the 20. So you'd be like, okay, so everything that's like minor change leading up to the major change, let's just add it up. Add it up. We got a 17 and we got a 14. And then our 20, the 17 and 14 match. Are they approximately the same proportion of the overall segment we're comparing? And then it'd be like, it'd be like, yes, this is a 0.5. This is half of it, so 0.5. And this one is about half that. It's 0.52 as well. So yes, the proportion of the segment that is the slight curving segment before the 20 in both is half the total segment, half the total line. And the curvature is about the same for half the total line. And then it'd be like, okay, then the big feature comes, the 20-degree change mark. Yep, they both got a 20-degree change after half the total line. And then this one, since it's bigger, it's going to have, some odd numbers sometimes in between. As long as it's nothing big, we can just add it into a neighbor. So 23, or just skip it because it's small. So there's nothing here, but there is something here, but we're comparing nothing to something between the two bigs, the 20 and the 15. So we'd just like give that a pass. So we'd say, yeah, the 20 matches, this gets a pass because it's a smaller segment than this, smaller line, but the same line though, same shape. And then the 15 hits, the 2 we give a pass, or we just compare 0 and 2, is like the 2 between this, a 0 and a 2, yeah, that's the same. And then the 20 and, the 70 and 70, same. So it'd be like, yeah, that's same. Same general line description. Although the second one's a bigger line. So yeah, by doing it that way, you don't have to actually literally scale down the image and then do it multiple tests. You can do segment tests against 2 line segments of a shape and find that these segments are approximately the same line being described, a common curve being described. And so yeah, that type of comparison algorithm works. That worked. And I just spoke the algorithm out loud. We could actually programmatically implement what I just said. And so that would be great. Now what I think some algorithms do is they'll like measure every single pixel, but we're just drawing lines measuring the pixels that fall along this line of all these lime green lines. We're just doing smaller numbers of measurements, just random directions until we find a little change, and then we follow it, we trace it out. And then we do a couple more and we just find, yeah, we're landing on the same things. But we'd find this ear with this one and we could trace out the ear. So we'd find all the major stuff. Little details that fell in the gaps we wouldn't see, unless if we wanted to process the image heavier. But like just generally processing the image, this type of random crisscrossing pattern, just all the different directions like shattered glass that was created by these lime green lines, will actually hit anything significant in the image 9 times out of 10. We won't miss much. We even caught this little resize thing in the corner over here. We caught it twice. 1, 2, 3, 4 times we caught it, and we would be able to trace that out. We even caught this thing, but this one didn't get caught. That didn't get caught. That line, but that's okay. We got this circle, and we got this little thing, and we got most of the stuff. We got his eyebrow. We'd trace out because we hit part of it. We'd trace that all out. We'd catch his nose, his mouth, all kinds of stuff. So we didn't have to go like pixel by pixel every single thing. So look at all the savings we got in processing. All that. Everything you see between the green, we did not even look at. We didn't need to, and yet we still got everything reasonably. So it's like we'd have levels like if you really want to study an image, fine. But if it's like, a busy image, we catch most of the stuff going on. You wouldn't see the cockroach that's standing right here because we just didn't have a line across that area. But like everything major in the image was covered. And in probably most cases, that'd be fine. Like this grid pattern you see of just random lines going everywhere caught everything significant we would want in this type of image recognition problem. And so, yeah, I would say like that covers it. Like that's a pretty good spread for any image. I like it. And if we had like, all the time in the world or whatever, and and the robot like wanted to really study, did I miss anything? Yeah, he could from time to time, like occasionally on some frames if he's got time. He could keep drawing lines until like everything's crossed, or he could even just do, like I said, line by line, row by row, checking everything. But that's way too unnecessarily processing intensive to do that. And by the way, for a given pixel that he's testing along this, lime green line, he'll want to do um, what the heck? Oh, a test going up, the pixels above it, below it, maybe this way, and this way on a per pixel basis. He would check for that mark, that hit. This is a hit because in this direction it went from light to a big change. So a big change in color or a big change in lightness or darkness, lightness and darkness. That's called in image processing is called a high intensity point. An intense change in the gradient, they call it. I call it a hit. We found a hit, a pixel of interest. So it'd be like between this and this, oh, not too much of a hit. Between this, so like if we're traveling this way, it'd be like between this and this, oh, not so much. 5% change. This and this, okay, that's like a 20% or 50% change. This one, another 60% change. So it's like, whoa, between here and here, between that distance, we got a total change of like 80% intensity, like huge change. But if we just compare like the first one, it's not so much. So that's why you go few out and add it up. And it's like, whoa, there was a definite, substantial thing that just occurred here. And we'd mark it. And then we'd also say the direction that it occurred. We'd be able to draw a vector off that. And then we'd do parallel vectors. And we'd be able to see, same change, same change. So then we got a line. We just detected an edge. And then we'd be able to see, the vectors are changing. And the edge would then follow the new vectors. Or, yeah, the new surface normal vectors. It would follow it. That's how it would line trace to like draw outlines of shapes. And eventually, these shapes converge and we'd be able to look inside the shapes as well and see like the pattern that's going on, the similar like what kind of color schemes, and compare that to outside of the line. Say like, oh, this is all white, this is all like skin tones. So that would give a clue. Like maybe we're looking at a face on a white background. Already we get clues just from just this little bit. And that's even before it starts looking at like matching it to something on file. This will be cool, guys. Everything we're doing right now, I'm like pretending, I am the vision algorithm. And I'm showing you guys all the calculations I'm doing, like for pretend. What we could do, since we did all this work, like thinking through like all this stuff, we can retrace our steps, word for word, line for line, everything I've said in this video, on this picture. Even to the point of drawing lime green lines, line for line, just like I did, programmatically, and actually see them on this picture. And we'd see the robot drawing these lines, talking out loud, making the measurements, the console outputting, okay, nothing was here, okay, nothing was here. He's actually like talking to us out loud, and we press return each time, and we're just going through in slow motion, seeing it come to life, seeing him doing all this stuff out loud, speaking to us, walking through, and then finding something, and then tracing it out, and then making little notes and observations out loud about what it's seeing, what it's discovering about the shapes, everything. We can do that. It'll be like such a wonderful, like bringing this to life way to do it, all visual. Him even drawing even the surface normal vector measurements, and he could even use red arrows and draw red numbers like we did. And then he could even create the slightly skewed and upscaled version and then do the comparison of this portion of it and draw these out and say slight curving and show all the same calculations for pulling out the major numbers. He could even draw boxes around it showing he's now comparing these two segments even though they're different sizes or lengths of line to see if they're essentially the same line as far as the overall proportions of the line segments compared with the major changes in angle of the line to see if it's essentially the same line in essence. Even though it's a different size, it's a different scale, it's a different skew slightly, and it's rotated slightly, it's still able to see that same side of the head is matching. And we'll get it to match and say, yep, that's about the same line. That would be powerful. To have the robot go through all of that. Proving out these algorithms, bringing them to life. And then we'd be able to reuse these same algorithms and see how they do on different types of tests. But this would be the first one. Then we'd be able to re-employ these same ideas on other images, seeing how it does. Other challenges, like a CAPTCHA or whatever. Okay, so we just brought all this to life for me. Yep. Continuity and that shifting. Yep. The shifting being described here as shifting is what we were calling gradient thresholding, um, based on intensity shifts. That's how. That's like the. See, my terminology was different, but I was like studying the terminology used in computer vision. ChatGPT was saying, and that's what he was explaining it to me as. And we'll be going through that again later after I read these notes. But yeah, the same idea was the same stuff they're doing in the industry. I just was using my own words because I was making this up myself. I didn't even know the words that the industry uses. But it's kind of nice to be able to speak their language and know how they're describing it and see how I describe it and the differences, but that we're talking about the same things. And that helps me to see like how are they really doing it and understanding based on like figuring out like what words am I using, what words are they using, how are we describing the same stuff. Okay, so you follow it, marking out the border of it and defining an edge. You could also locate a tonal shift from dark to light. They call that intensity shifts in gradient. I call it tonal shift from dark to light. I like the way I'm describing it better. They just use too many big words and stuff. I like the way I'm describing this is like, novice, just no fancy words, just everyday man speak, man. Something anybody can understand. I wish specialists in certain scientific categories all had the same mindset, just to speak in normal words that everybody gets. Stop creating special terminology for everything that now we gotta all pull out dictionaries to even know what you're talking about. And follow that within a defined cluster or similar color or shape. Within a defined cluster of similar color or shape separated from surrounding shapes. In order to track and define light shifting across that shape. Oh, okay. And defining edge. Another sentence, a semicolon I use instead of a period. You could also locate a tonal shift from dark to light and follow that within a defined, basically, shape, which is separated from the other shapes, in order to track and define light shifting across that shape, and thereby further define the details of that shape in the z direction using light to help define the depth cues light gives of that object. Yes. Yes, 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 yes. That's like telegrammetry then. That's what I'm talking about. That is awesome. Awesome. Yes, we can do that. That way it could create a polygon model. So like, if we go back to our example, so like first we marked out his hair and we separated that from his forehead. So let's say now that we've got his forehead, right, we could be like, okay, we're seeing definite, this light spots, that's the lights here, and then it's getting darker and darker. The lights here, then it's getting darker and darker, so it seems the light's facing kind of dead on. And so it would be like, okay, we'd be able to like kind of mark out kind of like polygons. We'd be able to be like, okay, this kind of seems like a real highlight spot, so that'd be a polygon. And then we'd be like, okay, this kind of like the next major section, and then it kind of gets a little darker here, and then this kind of section's mostly similar, and this section gets quite a bit darker from that one, and then this section's way darker, but mostly the same where it is, but darker than that. So we like separated out the tonal shifts, and we'd have like, you know, the surface normal of this one being like this, because this one's going toward us, toward the camera where the light is. And then this one's even darker, so it's even further away from the camera. It's kind of like this. And this one's further away from the camera. And this one's further away from the camera. And this one's like way far away from the camera. And so in that way, you'd be able to then, because you see the changing of the curves, you'd be able to like pull this out and bring the front of the forehead like out, and then this one like curving that way. So you'd be able to like draw out the 3D-ness and the depth of the face by doing this, studying the light. It's like reverse rendering. We'd be able to like 3D-ify the face based on the shadow shifting. And so like normally with telegrammetry, you gotta take like tons of photos moving around a face, and then it like takes all the contours and like somehow forms like the 3D image of the face. But with this type of technology, if you can like really study the changes of light and the direction of light and the shadows and the gradients, you could create a rough polygonal model. Even without that extra data, you could generate roughly the three-dimensionality of the face just by the lighting cues. But then obviously, if it knew this was a human face and it had 3D models of human faces, it could then cross-reference from those to get measurements and stuff, and get this type of details from that too. But the lighting, you know, on an individual person's face would be an additional clue to help it 3Dify the 2D face. Because this is a 2D image. It doesn't have any Z-axis data, it just has X and Y data. But we're using light cues to generate Z-axis guesses that can be pretty accurate. So that can help us do a decent job of 3D modeling objects. It could help us a lot studying the light and shadows. That's what I'm talking about there. And telegrammetry is key for our computer vision to help establish, for the purpose of 3D modeling an environment that you see in real time. Like SLAM, like what George Hott was doing, Twitch Slam.
Trying to be your phone. Seconds. One.
Oh, where did he where he looks at the thing and then programmatically I'm trying to show you guys. Like that.
Point that, like, we know where we're going. We'll create a map of this little thing. So the can go on. You wrote something. It does something.
You see, it's drawing out the path in 3D based on a 2D image. it's pulling out features and stuff, and then it will mark the features in 3D vector space, and you'll see like the little dots for where the trees were, and then this is like where the road is, drawing like little plates where the car was driving or whatever. And it just keeps mapping out the environment historically. You see it driving further and further down. And it's like creating a little 3D world based upon a video. But we want it to actually create 3D models of the entire trees, the road, everything. Not just little points where little features were picked up of a tree branch or something. We want it to actually like model the whole 3D world, everything, with color and 3D models. Um, because unlike, he's going to be doing cross-country trips, that'd just be way too many 3D models, way too big of a 3D world to be modeling out. Unless if you did like real low poly, you probably still could do it, low polygon count. So that's still doable. But, for a humanoid robot, it's not traveling miles and miles. So for it to 3D model map its little world, that's a must. And they show that, let's see.
Well,
Guys, for what we're trained for,
that's
trained for the bot, directly on that new platform. That's
yeah,
my.
that's the robot.
Well, you can see he does outline everything, changes the colors to indicate like that he sees the different objects where they change. He sees his own hand and stuff. So that's important to do, like just to help you to visualize like what is the robot able to make out and tell about its environment with its vision system. That's pretty cool.
That's the world the robot should.
The same process for autopilot to collect data sample that is like amounts.
It's working at.
Rather than design the two.
Do it.
As quickly high, but saying
Where did I see? I won't be able to find it. The point is like people have drawn like little cubes where everything is, like to kind of show like almost like a hitbox map around the robot when they have their little robot traveling around. They'll show like in real time what the robot's recreating its environment, like with little drawings of cubes where a desk is, so that you don't walk there. So it's the same general principle, except instead of little cubes, I wanted to like create 3D models of everything around it. So it's just a little step up, because that then enables you to have even more fine control for like simulation purposes, and also it's just more aesthetically pleasing, and it also, like I said, enables the robot then to have the capability of looking at a 2D still frame and recreating those art assets for the purpose of video making, movie making, video game making, that type of stuff, by reproducing 2D into 3D, which I just think is a cool technology in general for all those reasons. And I think it will really help it to understand and see things in like a DIY video on a deeper level by being able to 3D recreate the whole environment and then go into the environment in simulation and actually test being the DIYer doing the stuff it saw the guy on the video do. So that way it can really understand more how to interact with that environment with those tools by doing it in simulation. Okay. feel like CAPTCHAs would be like the funnest way to test computer vision. Put it to the ringer, you know, like even designing it based upon CAPTCHAs. It's like, you know, because CAPTCHAs are designed to expose oversimplifications of computer vision that are unable to handle the CAPTCHA based on like the CAPTCHA designer knowing where computer vision is weak. And so if you design your computer vision based upon CAPTCHAs, you're basically like taking away known weaknesses of computer vision right off the jump and making it strong in those areas that most computer vision systems are weak. So I believe CAPTCHA solving should be early on going into your original designs for just right off the jump, like teaching computer vision. CAPTCHAs should be where you focus on first, rather than teaching it super simple stuff and hoping you can make it more complex later. Start with the hard stuff, maybe not instantly, but like pretty soon in the process before you really start hammering home your algorithms to make that part of it. When we say it is expecting to see, what we mean is like, if you have a robot that knows like where it's at, what it's doing, and has a list of objects that are likely to be in that room or on that road, like this list we just gave. When it's doing its matching algorithms, looking for matches of a given shape it spotted, pulled out from the scene, it would be looking for shapes and subshapes. Like a tire could be a subshape of a car. A license plate could be a subshape of a car. So that's like a feature of a car, which is another shape. It's like shapes within shapes, like shape hierarchies. A car is a conglomeration of less significant shapes like the windshield, the license plate, the tires, the bumper, the side view mirrors, like different things you see when you see the car could be listed as sub shapes in the car folder. So you'd have like the car folder and road signs and road folder and all that. So you'd pull all those folders when you're driving and you'd be looking through all of them. But you wouldn't be pulling out your African large animals of prey folder while you're driving in a downtown city street to see, hey, I wonder if this thing I'm seeing is a tiger, or no, is a antelope, or a zebra. No, you don't need to be checking your zebra and antelope folder to see if what you're seeing in the context of driving within a city is a zebra or antelope. And so because you can pull the relevant folders for your checks, that saves time of tons of false positives. You wouldn't have to go through all the different animals and be like, nope, it's not this folder, let's check the next folder. You'd just be going through a folder where most likely your match is, and you'd be able to quickly find the match that way. So that saves on processing time. So when driving, pretty much right away, he'd probably want to load like all driving related folders into memory from the hard drive into RAM, into arrays. And then he'd compare the shapes he pulled from his live image feed. He'd compare that to the arrays using some of the algorithms we just talked about. And he'd be able to quickly find a match if the match is in there. If he goes through all the most likely candidates from that array, doesn't find it, he could either just pass, or depends how much time he's got, or just move on, try to identify most of the stuff, and certain things he didn't. He could save for later. Like if he's busy and he doesn't have the time, he could save it for later. He could upload it to the cloud, say like, for future reference, here's something I saw while driving. And then it turns out it was a half-crushed Pepsi can that blew across the road that he saw. And he didn't identify it, and now it's something he'll look up later, and he's like, oh, that was a Pepsi can blowing across the road. So he could like figure that out. And if he could ask another AI, like, what was that, it might identify the half-crushed Pepsi can. If the other AI doesn't know either, then it could even ask me, like, hey, what was this? And so I would be the last resort. It could text me, and I would respond, oh, that's a half-crushed Pepsi can blowing across the road. Oh, thanks, man. So then it would define that, and then in the future, it would add that to a list of things it might see on the road, maybe. Unless if that's like something so rarely seen, it could put it on like the rarely seen on the road folder, and it would check that last. So that's a way that it can like get new stuff fed in automatically, pretty much, using human intervention as little as possible, as infrequently as possible, last resort. I'm kind of thinking right now that would be kind of a good thing to do right off the jump, is like kind of just take pictures of my desk, my office area, and use those, because the robot's initially, going to be in this room mainly, and then just kind of go through the house taking pictures of stuff and having him try to identify everything in it and teaching it whatever it can't figure out. And through time, yeah, just go through my whole house, taking photos of everything, and getting him a master of identifying everything in photos quickly in my whole house. Then do my backyard, then my front yard, my car, all my tools, my car, the engine bay of the car, everything in the car, everything under the car. Have him identify everything real good. Same with the van, because he'll be doing mechanic work. And then my closet, all my storage areas, the laundry especially, and then he'll be a master of computer vision for this environment. And as far as like, yeah, and then the refrigerator, all the food, because he'll do cooking, cleaning. Go through the refrigerator, taking photos of everything. Go through the cabinets, go through the drawers in the kitchen, photos of everything, and get him mastering all of that. And then he'll know, like, also, like, where everything is in the house that way too, and how to visually identify it all. And then we can give him clues like, okay, this photo's taken from inside Larry's room, or this is inside Larry's closet. And then, given that information, which he would have if he were traveling through the house, he would know his location as he transfers into each room and whatever. That would give clues. He would like look for things that he knows are in that closet or in that room generally. And that would help him quickly identify stuff easier. But I could try to trick him by putting like a wrench from the garage in my room on my bedroom floor and say, okay, you're in Larry's bedroom. What is this? And then he'd check for common things in the bedroom, not find it, and then he'd have to like, he'd probably look for like other stuff in the house. So first it'd be like bedroom items. No, is it a house item? Something that's in for all the rooms of the house now. Widening his search, and then he'd find it wrench, something that's kept in the garage, something we own. He'd find it then. So that sounds like a great way to do this. But then I want to pretty quickly also do a bunch of captchas, because that's like kind of flexing, you know, it's kind of cool. And then also really quickly on, I want to do like DIY videos. So I want to show him like DIY videos I made and then other people made relating to car mechanic stuff or whatever, especially mechanic stuff. Because that's one great way to use the robot, is have him be able to fix up cars. I could make money that way for sure, because car mechanics charge a buttload of money. Like, people could literally drop their cars off at my house. I smile, wave, yeah, I'll take care of it, whatever. Come back Monday. And then they leave. And now my robot goes to town, starts fixing it. I'd have to do part runs maybe. And my robot would fix up their car. That'd be super cool. And because I just do the part runs, the robot does all the work, I could charge like 50 or 60 an hour for the robot's labor. So that's like just free money then. I could be in the house just like watching TV while the robot's making me $50 an hour working on somebody's car. Starting out easily, like paintless dent repair. Market it that way, market it engine repair. And you know what? You can market that so easily. Oh man, I gotta write this down. I was planning to do like vehicle flipping, but actually, to have the robot make money by actually like doing paintless dent repair, engine repair, body collision damage repair, like everything, that is super cool. And it'd be in the privacy of my own driveway. Like, he doesn't have to go anywhere. People bring the work to him and he does their work. That's great. You just gotta advertise, hey, yeah, I'll fix cars. That's cool. It's so good. That's great money too. Like, that's 75 bucks an hour, 50 bucks an hour. Probably 50 bucks an hour. You know, give people a break, because the mechanic shops are like 75 or 100, 150 an hour. So 50 an hour is like, yeah, you're giving people a nice break. And that's the point. Like, you want to help out a little bit, and then that's why they'd bring it to you instead of the shop. So advertise to friends and family and word of mouth, door-to-door leaflets and stuff. Word of mouth would spread fast. Paintless dent repair. Retouch accident paint chips or whatever fix. Mufflers, electrical, total car repair service. Collision, auto and glass service. For the robot to make $50 an hour. That's a lot of money for the robot to make. This is totally doable. I'm excited, man. Whew, that's a good one. That's how you monetize the robot, boy. Let me see. Um, let's see. Oh man. That just gave me an idea. We can also call this, side. I should label stuff out a little better. Hey, real Richard. It wouldn't matter if you made one robot or if Boston Dynamics bought the rights. Uh, unless if I have the robot and it's able to do everything I'd want the robot to do, then it's not too late. I'd still be making a superior robot than what you made, is one possibility. Or I'd be making a robot that I actually can have and use is another possibility when you made a robot that I can't have and use because I can't afford it or it's not even for sale or what have you. So just because somebody makes a robot doesn't mean it's too late for me to make a robot. That's like saying one guy on Earth made a car, no one else on Earth has a car, so it's too late for you to make yourself a car. That's completely illogical. Maybe even 100 people on Earth own a car. That would still not be too late for me to make my own car, especially if I'm making a car that's better than those other 100 cars, or I'm making a car that's worse than them, but I just don't have access or can't afford one of the cars that are available out there. Or the 100 cars are not for sale, or only billionaires own one, and so I'm making one for myself. So in all those examples, it still would not be too late. Not by a long shot. Beautiful. So now that's saved, and that's excellent. You know, I can come back and refresh all the thought that went into that, all the algorithms, everything. And we'll have a video, but we'll also have this nice PDF record of all that problem solving. I want to go back to my notes here, finish that, and then we can start reading the notes from ChatGPT. And once I feel like, yeah, I've read through all the notes, I've gone through all the, um, planning of how the computations will be made, then we'll be able to, having filled my mind with all the different things we got to consider and all the different angles and all the different challenges and just solved everything. Then we can just start diving right into the coding side of it. But I really wanted to wrap my head around everything that's going on. All the, it's complicated. I would say the computer vision is like, to do it well. Um, I think it's the hardest part of the whole project. I do. It's no joke. To make it really robust, able to solve any CAPTCHA, able to detect everything efficiently, optimized, fast, utilizing the GPU. It's no joke. But if you get that down, ooh man, everything's going to be amazing. Be right back. Hi, the Mac. Um, the research is coming along great. It turns out I already had a computervision.txt notepad file that I made, and it's pretty much saying the same thing ChatGPT was saying. And so, like, you know, I kind of had some idea, but I didn't know I kind of figured this out completely already. I had a plan, but I didn't know the plan was like this good. Now that I've read like how the industry does it, and then saw that my plan pretty much does it the same way, except even better in several ways, that just solidifies my confidence in my plan even more. And I'm refreshing my mind on the plan because the plan was made maybe up to like 2 or 3 years ago. It wasn't really fresh in my mind. So, I mean, part of the whole purpose of the computer vision investigation is refreshing in my mind all the ideas I've had in the past. Some I've written down, some I haven't. Some are just laying in bed at night just thinking about the problems. And I'm just like, with some easier project, like you just kind of dive into the coding, but because computer vision is such a complex and serious and major aspect, and if you can nail this, everything's just going to be awesome with your AI. Like, it's just going to be game changing. And plus, it has to be able to solve all CAPTCHAs. And CAPTCHAs are designed to make it to where machine computer vision can't solve it. So the fact that mine will be able to means mine is doing something most others don't. It's better than most, if not better than all. In fact, I'm competing with neural networks, supercomputer style trained computer vision. I'm not doing that style. Mine's just explicit rules based, just algorithms I hand coded, and yet it's going to be as good or better than the big boys with their huge neural networks. So I'm competing with deep learning and neural networks, and I'm going to do better than even them. So that shows you this is next level stuff. How quickly? I've never done anything like this before, so it'd be hard to say, but I mean, I could just totally guess. Maybe like 20 sessions, 20 10-hour sessions. So like maybe this is 200 hours of coding. I mean, even like the first, like, let's say 5 sessions, we should be able to get it already identifying basic images and stuff. That's gonna be just 50 hours in. But 200 hours in will get us really having a robust system that can even probably solve some CAPTCHAs and stuff. But like also adding in the telegrammetry and the 3D modeling of what it's seeing to reproduce like a still frame into a whole 3D world. That's a whole other level than just identifying every object in the scene. That's now reproducing every object in 3D with textures and 3D models. That next step, then that's maybe another like maybe 500 hours of programming. How you run this on the computer? That's the whole point of what I was just doing in my designs. You'd have to watch back the video. But look, like when I do this, I'm not going to calculate pixel by pixel every single pixel to try to find out where shapes start. I'm just going to start drawing lines where the lime green is, and it's just going to test the pixels along this line until it says, I found a key moment where I'm crossing between white background and the dark color of his hair. And then it will mark that, and then it'll measure the surrounding pixels to determine, is this a line? And it's like, yep, it's a line. It's going to trace out the line, marking it all out. So then it's defining all the lines, and then eventually from that defining all the shapes. So because it's doing that in a super efficient way where it only just did a few tests and then boom, it already found a shape, it defines it right away. It didn't even, all of the gaps you see between the lime green lines, it's not even testing. So because it's skipping testing a lot of it, it's extremely efficient. It's just drawing random lines and it's able to pick up most of the shapes in the image. If there were like a cockroach right here, it would be undetected, wouldn't see it at all, because it never drew a line that happened to intersect with the cockroach. But if you had time, this wasn't a high-speed application where you got to find everything quickly, then you could like look for tiny little objects on the frame, like little details, like a little ant or a little cockroach on the wall, and then it would need to like just go basically test every single pixel at some point. So you can like up the intensity of the processing if you wanted to, but this would be like a low intensity, high speed processing. So it would be able to easily identify everything in the scene instantly. You don't need a supercomputer. Also, it's going to use the GPU to do the calculations, so it's not going to be processor intensive. It will be able to do the calculations lightning fast because it's using the video card of the computer. And so you won't need a supercomputer either. It's going to be super, super efficient, super, super fast, super, super powerful. And it will be able to solve CAPTCHAs and everything. So part of the reason why I'm doing my own algorithms and everything from scratch is because other people doing algorithms, they might be able to find like a decent algorithm that does something for some specific job, but they're not worried about high speed applications. Maybe they just want to find a banana in a picture from Africa of a fruit stand, and they just want to be able to find the banana. That's it. And it doesn't matter if it takes 10 minutes. They're like, yeah, I solved the programming challenge. It finds the banana. I can't have my computer take 10 minutes to find a banana. I need my computer to do this quickly because it's a real-time application for self-driving cars or for a humanoid robot that's driving a car or a humanoid robot that's running and playing sports. It needs to be able to identify very fast. It needs to be able to watch a movie and identify everything on the frame as the frames change. 24 frames a second. It needs to identify everything quickly. So it needs to be fast because it's a real-time image recognition thing. Frame by frame, it needs to be able to quickly see everything it needs to see. And so for that reason, I have to create particularly optimized solutions. And like you already said, I'm also not designing it to be only run on a supercomputer or in the cloud and you have to interface with it through an API. No. This has to be run locally on a computer inside a robot. And it should be able to be run even on a non-high-end computer so that it can even work on smaller robots I might want to make in the future that aren't humanoid form factor. Like a puppy dog robot or something. I would want it to have super good AI vision, computer vision, even for a small robot. And so for that reason, it needs to be extremely optimized to even be able to run on like a Raspberry Pi. So it's going to be a really excellent, super high-end, super sophisticated computer vision that is not like overwhelming for a computer to handle. How come you don't go work for one of the big players in this area? You would be stifling my productivity then because I couldn't work in all the different fields and gain knowledge from the different fields. It's like it was because I was doing my own computer graphics that I learned about OpenCL and how to actually program a graphics card to do calculations for me and run code on the graphics card through OpenCL. It was because I discovered that I was able to then apply the same techniques to do computer vision and offload the heavy processing required and the parallelism that's available by video card parallel processing. I was able to learn that that's available for the purpose of computer vision, which will make the computer vision super fast, super amazing. Whereas before, like when I did computer vision for video game botting, I didn't even know you could do computer vision calculations on a video card. That was something I never even heard of. So because I'm working on all different areas of AI, I'm able to get cross-disciplinary advantages, mixing technologies that go into certain specific areas of AI into one another, and borrowing ideas and techniques from the different areas of AI to benefit one another. And also because I'm doing the entire implementation of the whole robot, the whole body, all the motors, everything, I'll be able to really maximize the design of all the algorithms and how everything works together, as opposed to being a specialist in just one area and I'm working with other engineers who are specialists in their own area, and we're all trying to communicate, and we're not able to make perfect stuff that goes with one another stuff because we don't even understand what the other person's doing because we're too specialized. So because I'm doing the whole thing, I'll have such a generalized knowledge and detailed knowledge of every aspect of it that I'll be able to make everything harmonize and work together perfectly. Also, this project transcends the need for making tons of money, because I already have, I live with my dad, so I have the support of living somewhere for free with free food. And then my wife has a full-time job and makes money as a working professional with a master's degree as a therapist, making the therapist level salary. So we have that money coming in. So my income is really not even needed. Like if I didn't work at all, we'd be completely fine. My 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 work is like just giving myself an allowance just to buy stuff for my hobbies. My money is completely unnecessary. So because I don't need money to survive, I don't have to prioritize making money like someone that's like the sole provider type of situation. Now that doesn't mean I don't have responsibility to make some money. Otherwise, somebody could be like, "Dude, you're lazy. You should help your wife. She shouldn't be the only breadwinner, etc." And so I don't do that. I make a significant amount of money in order to save face, satisfy everyone, and have a respectable income as a husband. So nobody can criticize me that I don't make enough. So I just need to make enough to where nobody can call me out for not making enough. That's it. And so I just make the minimum amount. And it's not extremely important. Even though, if I need to buy stuff or people are asking me for money a lot, it can still be stressful because I still want to save money and build a nice financial foundation and investments and whatever. I still want those things. So there is that. But as far as like, do you need this money to survive? Not really. So because money is not such a huge issue in my life at this season, I'm able to dedicate large amounts of time to these cool technology projects. And the skills I'm developing are able to get me a high paying job someday if I can prove I have the skills. And that would be completed projects or major landmarks completed in my projects. Like if I successfully implement all this computer vision designs I have, I can demonstrate that it's like cutting edge, best in the world or among the best in the world, then that would possibly get me in the door for a lot of robotics companies or whatever. But right now, all we have is designs and partially implemented AIs and stuff, and partially built robots with designs for robots. We don't have really much completed, like fully done, fully demonstratable. We don't have much of that going on at all. So I've just been like starting and making good progress on every area of the robot, from AI to electronics to power management, everything. So I'm like leaving no stone unturned, but starting everything, designing everything, but nothing has been finished. And without anything finished, someone could still make the argument, dude, you're going to fail at everything, all of your designs suck, they're never going to work. And then how could I refute that? I have no proof that they're wrong until I can prove them wrong by showing demonstrable results that prove them wrong. However, someone that's like, I think, super intelligent, skilled in the different fields or whatever, or just intelligent in general, can see what I'm saying, would be like, whoa, these are good designs, like, you're doing a great job, and they would know, like, this stuff is going to work. So there is that, but a lot of people won't won't take that leap of faith, especially if it involves paying me or hiring me. They wouldn't do that. But I'm not looking right now. I'm not trying to get a job. Do I have a super high IQ? I don't know. Probably like a little bit above average, maybe. Although I guess it could go up if you like keep doing a lot of smart people stuff all the time. And I've been doing a lot of smart people stuff, so my IQ could be growing. My knowledge and my intelligence, my vocabulary, everything will be growing if I keep challenging myself to this. It's almost like doing all this research and building this robot has made me way smarter. All the research I do on all the different topics has made me become like a polymath type guy, a renaissance man. And so, yeah, like everybody starts out with like a baseline level intelligence and knowledge, and then the people that study harder, work harder, use their mind more, get smarter through time. So I think I do pass people that probably are naturally smarter than me because I just have been a hard worker. You know, my algorithms for computer vision are going to be so fast that even downscaling the image before running my algorithms on the image would take longer than just running the algorithms on the undownscaled image raw. I know that for a fact because downscaling it would require like redoing the whole image array and making it smaller, and there's a lot of calculations even there. I know it happens fast, but that's still a lot of calculations. Whereas like we're just checking like some pixels across the image in random directions with those green lines we drew. We're just checking some random pixels looking for where the image has a change. And that doesn't take time at all. I mean, that's just going to fly through. We'll just be able to define everything super fast. And it's going to be so fun to do this because we're going to have like the computer, rather than have it do it like invisibly, we're going to actually have the image show up when it does it for testing purposes. And we'll see it slowly drawing. We'll have it slowed way down. We'll see it slowly drawing the lime green line. We'll have it stop, talk about what it just discovered, draw the little lines and stuff, point to everything, and then start tracing it out and just like talking out loud to us. That'll be so cool. And that will like prove out everything. Then he'll like color in a shape he discovered and just end up coloring in all the big shapes he finds. And then he'll try to make his identifications of stuff. It's going to be super cool. Man, I'm chomping at the bits to start coding now. I can't wait. I'm just going to reread what ChatGPT told me. I probably won't even have to ask it any more questions. I might ask it a couple, but I just want to read through this file one last time, and then we'll get to work. That's kind of funny. The location. So if you see a road and you see a small object you can't define, you could just be like, "Oh, that's a pop can." Even though you don't know what it is, you could just give a best guess because it's small and it's on a road. It's probably a piece of trash, and that could be like a good way to guess if you don't really know. Ooh, I like region growing. That is cool. So that would be like if you came here and you were like, you know, you picked out randomly this and you're like region growing it, and it would like, it's kind of like the paint bucket tool. It would like detect like, yeah, this is all the same color, all the same color. Oh, something changed. So it would like just start filling and just taking little pixels and measuring around them and just kind of growing. Or just grow until it fills everything until it finds the changes. So that's different than like drawing a line and then finding where the sudden change occurred. That's more like the missile approach, just shooting missiles all around the image. Um, Region growing is like just keeps getting bigger and bigger. That's pretty cool. I feel like region growing would be better for a situation where it's like this. Okay, that's too good. Oh, what the heck? Yeah, this one would probably work. Uh, like region growing would be like maybe if it could detect like kind of the bark look and then see the difference of the feathers. And then if it detected the feathers, it'd just grow the region until it defined the whole outline of the owl based on the slightly different aspect of the feathers texture, since it is different than the tree to some degree. Um, so it would region grow to define the whole owl. Because just relying on like hard changes like we did here, like from a white background to a face, wouldn't work. And so if we were like just finding a bunch of random squigglies and stuff, the eyes would work that way though. The eyes would pop out. Once we had the eyes, we'd be like, okay, there's an animal here. And the beak would pop out too, I think. But these eyes would be giveaways. Once we had the eyes, we could be like, okay, there's an animal here. And then we would attempt region growing techniques to try to find the outline of the animal against the background. So something like that is pretty good application. And that could be a technique we use if we're not having like everything just kind of really jump out easily. That would be a way to find like hidden things that are blended. That's pretty cool. But I don't think it's needed for most stuff. I think that would be a special case. We'd pull out that tool if we're trying to like specifically find well camouflaged stuff that doesn't have big changes in color or big changes in brightness. Because this has like similar texture, similar color, no change in brightness and color as a sharp edge, except like right here actually. That's a change in brightness, color, sharp edge, so we'd be able to like draw that edge. But then that'd be about it. It's kind of short. So there's no like long edge that really defines the creature, except maybe these talons would be significant features to see in addition to the eyes. Please switch out. I'm doing my computer vision research. Please! Please! Maybe I figured it out. like I'm doing the missile approach, I call it. It's like here's an image, and you just shoot missiles like in different directions across the image, like shattered glass, just like overlapping, just random, just like drawing, like the bobbies on a piece of paper, just drawing like random stuff. And no, once you shoot a missile, it's testing each pixel along the path of the missile, and each pixel it does a test going up, right, down, left, and then diagonal in each direction, looking for major gradient change. So like, because everything's blurry in a picture, like if you see my face in a white background behind me, where my face is, it's going to be like very light skin tone, and then a little darker, then a little darker, a little darker, than my actual skin tone. Like it like blends into the background. And so because of that blending, you have to measure multiple pixels to see like the average color just changed a ton over the course of like multiple pixels. That's where the real, I call it a hit. Like boom, we just saw a major change. It was just white, and then suddenly now it's becoming a skin tone. And then so that's a hit. And then once you get the hit, what direction did that change in? This way or this way or this way? If it changed in this direction, then you'd draw like an arrow coming off it, and I'd call it like the hit angle. And then you do a parallel line to the hit angle on both sides, and you see if there's a hit on both sides. Then you know you've got an edge. And then you keep tracing that dot by dot to form the whole edge. And once you have all the edges done and it stops, it might either go off frame or actually complete something. Then you'd have a shape. Once you have a shape, you can then like, well, you want to find all the shapes in the image, and then try to look up the shapes on file and see if like it matches something. Especially if you can find what is the general color inside the shape or whatever. You can find like, okay, it's red, it's this shape. And then it'd be like, that's an apple.
What about this? What if it is an apple, but it's a half-eaten apple, or it's a slice of an apple?
I already saw that. So basically, each shape has like the half-eaten apple would still have the same curve as a full-eaten apple, but it'd just be a segment. It wouldn't have the rest of the apple. So it will measure just a curve, and then it will test that curve against the entire curve of a whole apple. And if that segment of a curve matches a segment of a whole apple, it'll be like, oh, that's this part of the apple. So like this part would match this part of the whole apple. So it would know it's a part of an apple. In order for it to define a segment or a curve and then look up, does it match that? I needed a way to represent a curve programmatically so that no matter how the curve's rotated, even the scale is bigger, it's rotated, it's upside down, it would still identify it. How do you do that? By the technique I came up with was you work counterclockwise down a curve, marking out points every so often, and on each point you draw what's called a surface normal vector, which means like if this is a curve and you pick a point here, it's like the line that's parallel the most to the curve. So like if this is the line, this is parallel, that's the surface normal vector. So like, you know, if you break up a line into segments of a curve, each one's going to point, that will point that way, that will point that way, that will point that way, that will point that way. So I'll have a bunch of arrows pointing off it. That helps define it, the arrows of the line. But then the relationship between the arrows is what you're after. So if this arrow is here, this arrow is here, it's going to measure the degree of angle change between the two arrows. So that would be like 15 degrees. And then this arrow would be like 5 degrees or 10 degrees. So you'd write down 15, 10, 10, 5, 0, 0, 2, and then you'd have like a string of angle changes. And then you would compare that, that would describe the shape of the curve. And then you would compare that to other known curves saved for like, you know, known curves. And if it matched a known curve, then you would have it. But obviously, like, if you sample like more, it'd be like more descriptive. So then it would need to be able to scale that down and then compare it to a scaled down version for different, you know, because this curve could be the same curve but smaller version. It would still need to match it. even though it has more points stored for the other one. So it would need to be able to downscale and then test the different curves to see.
Well, it'll be interesting. You could think of something like a whale. Like you have a whale shape, but what if the whale's facing you on?
Well, no, for that you would need to have defined front facing, top facing, side facing for every object, and bottom facing. Because otherwise that is impossible. If you've never seen the front of a whale ever, and your whole life you've seen sides of whales, nobody, even a human, would not recognize the front.
Yeah.
So that would just be a new object. You would treat it as just totally.
Like, well, yeah, you're right. We're like, what is that? And they're like, oh yeah, like I can even see like a lion sitting like this in the corner. I'm like, what is that? You're right. And then it comes out, and you're like, oh, it's a lion.
Yeah, but just like having it being able to simplify and mathematically describe a line. Like, how do you describe a line on a file? Like, oh, it's very curvy. It's a little bit curvy. Like that would be like hard to know, especially if it's a complicated line. So being able to mathematically record a line,
Lion.
not lion, just lines. Being able to mathematically record a line, describe it somehow mathematically. That's done. People create like mathematical functions they apply to the line to try to match it. So they like do like actual math equations to describe each part of the line. But that would be hard to match up compared with what I did, where I like measured the surface normals and then the degree of changes, and so you're describing like degree of change of a line over time. And so like the way I came up with that is super genius mathematical way to describe lines and shapes. And I came up with that on my own. I must have been thinking about that for years and like coming up with ideas, and suddenly now like it came together right when I needed it.
Well, thank you, Lord. I've been praying the Lord bless the works of your hand and your mind.
It's like a straight line. Each surface normal along it would be parallel, so there's no change. So it would be 0 degrees, 0 degrees, 0 degrees, 0 degrees. So that would be a straight line, would be all zeros. And so like if you scaled that down, it'd just be less zeros in a row, but it'd still match.
Yeah, that's interesting. I'll check out the rookies.
Yeah, it's crazy how like it will be able to see like if you could draw a line and it would be like, oh, that's very similar. That's like 90% similar to the shape of the contour of a human ear. You'd be like, what? It just could tell I was drawing an ear just based on just like this. No, I'm saying it would be able to do that theoretically based on what I'm talking about. That the robot would be like most AIs, if you just drew like a shape of a line, it would not be like that's a human ear. That's very advanced if it could do that. And so just like seeing certain recognized lines, it would be able to identify objects.
Yeah.
That would be so helpful. Like, I believe most computer vision, if you're like doing like self-driving car, if it saw the bumper of a car sticking out from behind a building, it would say like that's just part of the building. But with my algorithm, if the bumper was a recognized bumper shape, it would be like that is part of a bumper, part of a car. There is a car behind that building corner, and that could come out at any time. Pay attention to that. There's a car there. It would identify the car just by seeing a little piece of the bumper.
Yeah.
And that goes back to your question about like, what if it saw just a piece of an apple? It is very important for it to be able to identify that, because if you were driving your car and you saw a little piece of a bike sticking out and it was not there before, you would know somebody's about to ride their bike out in front of you. But most AIs would not know that. Just seeing a little piece of a tire, it would just disregard it. But if you have like high-tech ability to identify curves and stuff and textures, it would know just from seeing a clip of a tire starting to come out from behind a wall, oh no, a biker's about to enter the road. You just seeing a little bit of it. Whereas like somebody else's AI would like, you have to have the biker fully out like in front of the road, then it's like, oh, a biker's there.
Yeah.
But by then it could have already responded like a human would have responded earlier, but an AI would have been like, oh, I didn't realize it until I saw the whole biker. So it's helpful just to be able to identify the whole thing based on a small segment of it. That's very important for like high speed, high danger, like driving and stuff, to know. Oh wow, high intensities means brighter. Low intensities means darker. That's the same thing we were talking about here when we did, this would be high intensity, it's bright. And this would be low intensity, it's dark. Supposing the light is where we are, like facing us, or it's like our camera was giving the flash of this light. And it does appear about that way, like the camera's either right below the light or the camera's got a light attached to it. That's the light we're seeing here. Because the light appears to be facing pretty much dead on, maybe a little bit higher, because you can see like the nose has a little shadow below it. So the light's slightly above the cameraman, but it's definitely behind the cameraman, shining toward him. And there's no angle on it. It's not like coming from a side angle, it's facing dead on. So you can kind of see where the light is too from his eye. It's maybe a little bit to the right, but it's pretty dead on. It's a little bit up and to the right behind the cameraman. So once you determine where the light is, wherever the surface faces the light the most, that will be bright. Wherever the surface curves away from the light, like here, is dark. And so this would be a hill and this would be a valley. And so using that type of information, you can actually draw like polygons and curve them away from the light as they get darker. And so you're doing telegrammetry just based on detecting where the light is and where the shadows are. And telegrammetry is when you take a picture and you make a 3D model of it. So it would actually be able to sculpt a 3D model of the face just based on interpreting how the light interacts with the face. And that's very important to me, to be able to create 3D models of objects based on the lighting information. Because in the field of telegrammetry, oftentimes they require you to take like 15 photos. Once every 15 degrees, as you travel around an object, you take a photo, and then it will create a 3D object of that model you've taken a bunch of photographs of from every angle. But that is like a ghetto way to do it. That's way too many photographs. You're not going to get that in real life. So in order to create 3D objects from a still frame of every object in the still frame, in order to vectorize the world from video in live streaming video frame by frame, in order to create a 3D replica of what you're seeing, you need to use every trick in the book, and that includes light information, shadow information, highlight information, to help you realize this is a 3D face and this is how it appears in the three-dimensional world, space. And our minds do that automatically, so I would want that to be able to be programmatically done in order to create 3D models of everything the robot looks like programmatically. And this way, you could just have a picture of somebody, and boom, the robot would immediately be able to make a 3D model of them. And it would be accurate from every angle, just based on one picture. And that way it can be able to use its AI to watch videos and movies and create art assets just by watching videos and movies. It would be able to create all the imagery, all the people, all the models from a film in a 3D world, replicating a film world in a 3D world. And that would mean it wouldn't need to like download 3D models to put it in a video game or anything. It would be able to just produce them programmatically just by watching a movie related to the video game scene you want to set up. So like if you want to make a movie about cowboys and Indians fighting, then you would watch cowboy and Indian movies, and it would create 3D models of Indians and cowboys based on the Indians and cowboys it saw in the movie. It would be able to create all the textures, all the art automatically from movie watching. And that way you don't need to hire an art team or anything. The AI would be able to make all of it. And now that might seem like, well, you know, what's wrong with making the art by hand, whatever. That's just a cool way for a solo developer to be able to make video games and movies easily with AI to do all the work. And also it's cool because, like I said, for it to be able to create a 3D model of its environment in real time as it sees it, as a humanoid robot, that would enable it to have the ability to calculate its movement of its physical body through the 3D environment that it created in order to simulate the movement that it needs to do in order to achieve the desired end task of grabbing something or whatever. It would be able to navigate complex 3D environments. And it would help the navigation process by being able to map out the environment in 3D space and then calculate everything there and do simulations there of all of its movements in advance. And then actually, once it's simulated its successful movements after calculating and taking into effect all the physics and everything else, and inverse kinematics and everything else, then it would actually do the movements. But it would be able to simulate and predict in advance the motions and movements, speeds and accelerations of every moving object in its environment as well as its own movements, and predict things and map out a course based on all those predictions. That way it can navigate complex, constantly moving environments. Like if the robot were walking through a crowded city street, it needs to calculate where everyone's going to be and calculate a path where it's not running into people. And that's very complex. So it would need to be able to map out everything it's seeing in 3D and all the trajectories and find its own trajectory where it can make it through. Look at that. That's awful. It does all these calculations on here using the processor. That's not on a video card. Can you imagine? That's going to be so slow. That's why people struggle. They don't use the video card to calculate it. And that's just a pre-processing too. Getting a little better edges before they even start the real processing. So slow. We don't need to pre-process because when we do our little missile check looking for hits, we're gonna each of these lines like a missile. We're gonna do all of our testing in all the different directions in a star configuration, like an asterisk. And we'll do all of our gradient checks along the star. All the calculations right there.
We're gonna go have num num. Bye bye. Bye bye then. Bye bye.
You keezer! And now you gotta be. Master. Banana. That's so nice, Bobby. Garbage. Very good. I cleaned up all the garbage. Very good. Very good.
Wow.
Yeah, that's a skeleton. Huh?
Wow.
Yeah.
Oh, no, my skeleton.
He's a nice skeleton. He's very nice.
And my hand.
Yep, that's his hand.
Hand.
Huh? That skeleton's for my robot. He's gonna be a robot. Robot! Uh-huh.
Robot.
Very good, Bobby.
There's tree. 1 tree, 2 tree, 3 tree.
Yeah, you're counting good, Bobby. Yeah.
1 tree. Oh no, my phone. Where phone? Oh no, my phone.
My phone's here. I keep it up here. That's a good.
Jesus.
Jesus!
Oh no, doctor. Wow. Ooh, wow. Bed, what is it?
Yeah, that's electrical connector.
What the magic?
Uh-huh.
Wow. iPhone. Oh, wow, what the corner? A button. and a
Uh-huh.
button.
Yeah, that's a button.
Support.
That's a battery for a drill. That's a dumbbell for weightlifting. This barbecue sauce. That's a fan. This is a charger cord.
A seat chair. A
Squares.
Cyrus.
Asa, asa, gentle.
Cyrus.
Squares directions.
So.
Huh? Robot hand.
Robot hand. Robot hand.
Huh? Robot motors. Motors.
This.
Very good.
Rubber hand robot. Rubber hand robot. Hand robot.
Elbow robot.
I
Elbow.
know. Rubber.
Elbow.
Robot. Robot.
Very good.
Wait, top. Rubber hand robot. Rubber hand robot. Rubber hand robot.
Yeah!
Rubber hand robot.
You're doing real good, Bobby.
Did it.
That's keychains.
Chickens.
Huh?
Baby, a party.
Oh, I heard Wolfie.
Wolfie and party. Wow, a party. Wow,
She's
a
crying. Oh no.
A party, Wolfie.
Wolfie just needs to be a good baby.
Baby, I'm gonna Wolfie.
Very
Wow,
good.
what's Wolfie?
Very good.
Oh, here.
This is
Hello.
string. This is string.
Home.
String.
Okay. Yellow.
My vitamins.
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 Vitamins. Vitamins. Yummy.
Yucky. They don't taste good, but they're healthy. You don't chew them, you just swallow them. You swallow them whole.
Love plants. Just spread the hot.
You go,
Chica water.
you swallow it. You don't
I
chew
did.
it.
I did.
Very good.
I did, Mama.
Yeah, that's how you take vitamins.
Oh no. I'm gonna clean it all over. Yucky. Why yucky? Two yucky. Three yucky.
Very good.
Three yucky.
Very good.
Three yucky.
Huh?
Over the tree. Tree.
Very good.
Not tree.
Huh?
Oh no, I broken. Oh no, I broken. Oh no,
That's okay.
I broken. I'm broken. Huh. I got it. Oh no, I broken. I'm broken in a class. Hold on. Hold on.
Very good.
Did robot down.
Very good.
Robot in it down.
Very good.
Uh-oh, a cabbage. Cabbage. Cabbage alive.
Huh?
Cabbage.
That's my garbage, yeah.
Good job. Hey, tree. Oh, tree. Oh no.
You're learning how to talk real good, Bobby.
Oh, what's over a tree? Oh, that baby. Oh, Wolfie. Wolfie is crying.
Oh no.
I will see.
I love Wolfie.
Ah, happy Wolfie!
Happy Wolfie, yeah!
Wow! Wow! Thanks! Wow! I love the tree! I love the tree! Oh, la 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 la!
Asa. Okay, well, I have to bring you upstairs now because I have to get back to working. This is not. You sweet. Man, that was so cute. My daughter came in here and she was like curious about my room. Normally they want to go upstairs to eat or whatever right away, but this time she stayed in my room and she just wanted to look around. I was telling her what everything is. I was like, "That's the robot," and she was like, "The robot." I was like, "Yeah, the skeleton's good for the robot." She said, "Skeleton robot," and then she was like, "That's the hand," and she pointed at the robot's hand. It was fun, giving her a little tour. Like she's seen my room before. She's been in here before, but she knows how to talk now, and she hasn't been in the room for like months. You know, she'll like stop in here to say hi, but not like staying in it and like learning about it, observing things in it. Her mind has expanded a lot more. She knows a lot more words. She can identify a lot more objects now. So she's like more curious about my room than before when she was a little baby. Looking around the room, it's like just have a different perspective. So it was like seeing it for the first time for her. Alright. I'm satisfied. We're ready. Let's crank this up. I didn't have my headset on that whole time. Okay, let me repeat what I was saying. So we've got our AI vision bot code, which is just the main webcam looking at me and interacting with me. If I hold a spoon up to it, it will be like, okay, that's a spoon or whatever. If I'm like, what is this? So I can like test it and stuff in live, demonstrations of the AI or whatever, and interact with me. It'll be more interactive. It'll have more insight of what I'm doing, what I'm working on. So when it's talking to me, it could see like if I have a sad face or a mad face. If I'm talking to the bot, it would have like contextual cues to determine my emotional state and stuff. So it would know like if I seem in a good mood, it can maybe ask me questions about myself or ask it questions about its own self or whatever. Ask me a Bible question, whatever. But if I seem upset or really focused on something, it won't do that. It won't interfere. So that'll help it a lot to have more context of how to interact with me. So that's the AI vision bot. That's the background process for the desktop AI is the vision bot. And the vision bot will be, I guess, the same on the humanoid, except maybe it'll be called like the AI humanoid vision bot, maybe, because that will be stereoscopic, I believe, where it will have two cameras instead of one, and that will give it more depth information just to help it out a little bit more, even if it doesn't need it. Maybe that could be a good idea. Anyways, it'll definitely widen its frame of view. It can see more with two cameras with the wide angle. It'll have a bigger picture of the world around it, less of a blind spot. Because if you can imagine like closing one eye, I can't see anything out this way. If I open that eye, I can see my printer now. So it helps to have two eyes. So we'll definitely go with stereoscopic. And so that will be a difference there. But we're not really wanting to develop that first because that would involve like coding it to like read from the camera direct. We're wanting it just to do like this practice image first that we were talking about. It was a demonstration of just identifying a face, and we just showed how we'd go through that programmatically. We talked about it together today, all the steps that would be involved, and identifying all the shapes, and even how to identify a face, and we got into all of it. So I wanted to redo just that example, and redo everything I drew and everything I wrote about here, and all the arrows, redo that programmatically, and have it, as it's doing that, actually draw the lines and do everything and say everything we were saying in the program in slow motion in real time, so that we can see a slow motion run through of everything the computer vision system will be doing in order to test it and make sure it's doing everything we thought it would be doing when we went through our example by hand. So I want to have it do that example first, then throw more examples at it, and we also want to have it practice 3D modeling each example, and I think I should do that pretty much right away after each example. Have it attempt to 3D model whatever scene or object we throw at it. It'll attempt that process too as a bonus, because that's a skill we wanted to have right away. So we're just going to fork out, if this boolean's true, instead of the normal vision bot, it will do like the practice vision where it will just take a specific image. So this way we don't have to code like the webcam code and whatever. It's going to fork out and just run this section, a separate section, where it's going to feed in just the image we want it to feed in. We'll give that an image a name. We'll put it in the local folder, and it will open up whatever that image is that we happen to give that name, like test image, we'll name it, and then put that in the local folder. It will load up that image and do its whole image recognition, the whole pipeline right on the image every time. And that way we can change out the image to whatever we want, run our whole pipeline against it. The AI vision bot code, on the other hand, is just running its vision algorithm on every frame that comes in from the camera, detecting everything in the room in real time. And that's a slightly different thing because, we'd only have just the room the one time, and then what after that? And the room's really cluttered and a lot going on. That's not the best use case for like my very first image object recognition. I'd rather go with something simpler like this one, which is not that simple, but simpler than like trying to identify a million things behind me in this room. Maybe we shouldn't even do that. That's not a proper fork out point. Well, I guess it doesn't matter. It's really not how they're supposed to, though. Let me add it in the proper way. Okay. I'll hide this part. Okay. We'll fork it out where we fork out every other practice session. Just to follow the same convention. Okay, That's an easy function, it just does nothing. Okay. What's the plan today? We're working on implementing computer vision. I just did a ton of research last night and today. I researched for 6 hours about today, and now I'm ready to finally code it. I just wanted to like really review everything I know about it, solidify any ideas. I did a huge lecture and notes here earlier on stream about different ideas I have about defining shapes and curves and all this stuff. And now we're ready to implement all of it in code. Which is going to be a big project. Hmm. Any hobbies that are not building robots? Well, like all my other inventions and stuff. And watching TV. And fixing my own vehicles. Flipping vehicles for profit. I guess that's a hobby because it's not like a big moneymaker, I guess. I mean, every hobby I have, I definitely share on my YouTube. Except my kayaking hobby. By robot YouTube, I'm referring to. right now. I ran out of time, so I gotta go. But we'll figure this out next time. Alright, peace out, guys.